to all of you and all present here, and thank you for joining us at the International Symposium on Molecular Chemistry and Smart Materials. So I welcome all the speakers, Professor Jayant Kumar sir, Director, Center of Advanced Materials, Department of Chemistry and Physics, University of Massachusetts, Lowell, USA, Professor Amitabh Jha, Head Chemistry Department, Acadia University, Nova Scotia, Canada, Professor Virender Parmar sir, Energy and Nanotechnology Materials Chemistry Center, Department of Chemistry and Environmental Science, Medgar Evers College, the City University of New York, USA, Professor Sunil Kumar Sharma, Senior Professor, Department of Chemistry, University of Delhi, and Professor B.K. Singh, Department of Chemistry, University of Delhi. A warm welcome to you on behalf of entire Amity University in this good morning. I hope you will be enjoying the entire day for the today's program in this International Symposium of Molecular Chemistry and Smart Materials. So we are Amity Institute of Click Chemistry. We are Amity Institute of Click Chemistry Research and Studies. So as you know, Click Chemistry got the Nobel Prize last year in 2022, joining of two molecules with precision, speed, and reliability. The term click chemistry is coined by Professor Sharpless in 2001, and for an approach which was led to the use of few key chemical reactions to link together compounds that contain particular chemical groups. The reactions have a strong energetic driving force that ensures the starting compounds that react every time quickly, efficiently, and without creating unwanted byproducts. So that is the USB of this, that unwanted byproducts are not there. And it is a small time, it takes small time, maybe sometimes within 45 minutes, you get the product from the starting materials. So this philosophy is rapidly expanding throughout the world of polymers, material science, drug delivery, and even biological imaging. So to reach new destination, new avenues are paved. With the blessings of Founder President Sir, I received the Distinguished Fellowship from University of Nottingham, which was offered by Royal Society of Chemistry. And I went to work with John Moses, who is a student of Professor Barry Sharpless, and learned some of the biodiversity, base synthesis, biomimetic chemistry, and click chemistry. In turn, of course, I also helped him to learn some of the nanobioconjugates, nanomaterial compounds for drug delivery, for bioimaging. And then John Moses was invited in 2012. This fellowship was given to me in 2011. So after finishing the Distinguished Visiting Scientist Award, I came back to India. I apprised the faculties and the scholars, the members of Amity University, about the potential applications of click chemistry, and let us have some center of click chemistry. That was the idea of our visionary Founder President Sir. And in 2016, then the click chemistry was established under the aegis of Amity University. John Moses as the chairman of the institute, and few faculties started joining from 2019 onwards, whom I will be presenting in my slides. So with click chemistry, we have already introduced two courses, PhD in Molecular Science and Engineering and Masters in Molecular Chemistry. After this pandemic world, we thought that let us see the things in molecular level and let us name the course and again take the approval from UGC that we started the Masters in Molecular Chemistry. So with this, I start my slides, Amity Institute of Click Chemistry Research and Studies. You can see the images with John Moses and the faculties. When John Moses was invited in 2012, we bestowed on him Chair Professor of Biotechnology because my genesis was with biotechnology. I started my career as a faculty of biotechnology, and I received this Royal Society fund with biotechnology department. So the biotechnology was the department to bestow on John Moses, the chair professor. And since there were some faculties from nanotechnology working as a collated team member with my group, so the honorary professor was bestowed to John Moses from Amity Institute of Nanotechnology. So you can see here our founder, sir, the director, ex-director, the late Professor Srivastav, sir. And these are all the photographs when I visited Nottingham University. This is with Ian Jones in University of Oxford. And visit to Nottingham University with Ian Jones and other distinguished fellows at International Office. Professor John Wood, he's John Wood, whom we met in the Woburn House Square, London, working in the laboratory with John Moses and the members of John Moses, Dr. Pallavi Sharma Moses, who was the manager of John Moses Lab, the members, other distinguished members of different parts of India, IIT Madras, JNU, receiving the Distinguished Fellowship Award from University of Nottingham, Professor Sahara O'Hara, the Pro Vice Chancellor of University of Nottingham, giving me the award. To move on, we made John Moses the external co-guide of some of our students, and you will be happy to know that till date, John has guided 2 students as an external co-guide. So Dr. Deepa Suhag, she's doing wonders. Recently, she has received a huge fund with ICMR and jointly with Oxford. Dr. Payal, she's working as a team lead in University of Waterloo. We had several brainstorming sessions with John Moses and my research scholars. I said I started the department alone, and slowly in 2019 onwards, the faculty started entering into Amity Institute of Click Chemistry Research and Studies. Professor Brian Smith, who came to launch the Click Chemistry Research Program and beyond in 2017. Founder President and John Moses gifting his photograph with his wife and son, Glyn Sharma Moses. John Moses sparing some time in the brainstorming session with the Click Chemistry faculties and the collated members of Amity University. Yes, the Nobel Prize winner. When I started the department, Click Chemistry, people sometimes used to make mockery. Oh my God, Click Chemistry is a tool for making STM research. How it can be the department. But see the visionary approach of our founder president, sir, that at that time he visioned that yes, this will be one day leading the world. And in 2022, Click Chemistry received the Nobel Prize. And it's all known to you that Caroline Bartholdi, who really did bring the click chemistry within the cell without disturbing the mechanism of the cell. So Professor Barry Sharpless and Morton Mendel has developed the new strategy, that this is the strategy of joining molecules without undesired side product. And this is click chemistry, but using the click chemistry inside the cells without disturbing the mechanism of the cells was done by Caroline R. Bartholdi. So 3 of them jointly received the Nobel Prize in 2022. So a big round of applause for click chemistry for getting this Nobel Prize. And you may be happy to know that this is the first department in the entire universe, I can say, the Click Chemistry department. There are Click Chemistry Research Institute, but academic institute in the name of Click Chemistry, not only in the entire India, but the entire world. It is Amity Institute of Click Chemistry Research and Studies. So the Professor John Moses is the chairman of the institute, and his area of research is biomimetic synthesis, click chemistry, anti-cancer drug discovery, and chemical biology. He started his career with Oxford, with the degree with Professor Jack Baldwin, followed by postdoc with Barry Sharpless in Scripps Research Institute. Thereby, he joined Nottingham University, and after completing his 5-year span in Nottingham University, he moved to La Trobe University in Australia. And after that, finally, he is now the chair professor of Cold Spring Herbal Laboratory, which is ranked #1 by Nature. And it is our proud moment and privilege that John Moses accepted to become the chairperson of our institute. Moving on to the next slide. I was appointed at that time the director of Click Chemistry, and the area of research was injectable hydrogel, carbon nanohybrids, hydrogel nanocomposite molecular science and research, and materiobiology. I work in the pronged approaches of materiobiology, Click Chemistry, molecular science, algal nanobionics, which I have developed. For the first time, people used to know about plant nanobionics, but I developed in Click Chemistry department algal nanobionics, drug delivery, bioimaging, and biosensing. And I am happy to tell that I'm also the editorial board member of Scientific Report Nature and associate editor of Biocatalyst and Biotransformation. And I entered as a fellow of Royal Society of Chemistry in 2021. The area of work, as I said, bioimaging, diabetic wound healing, scarless healing of second-degree burn wounds, stem cells, migrations, differentiation without any growth factor and inducers, which reduces the cost of the experiment. So the work always not only doing the basic science, we think in Amity University, we are mentored by Professor Selvamurthy sir that do something so that it can be helpful for the society. So we do work with the approach of societal benefit, and we can go for the technology transfer. So now one of my product is our incubator team and our team of Dr. Meenakshi, who is trying to take this technology to the industry, that without growth factor and inducers, how you can generate cartilage, which is very, very important because most of the population and the middle-aged population, they're suffering from arthritis. So we are also working in targeted delivery, drug delivery for the treatment of colon cancer. In 2020, when the pandemic was there, we tried to develop 9 different type of bioisostars, the Click Chemistry department, and you will be happy to know that that work was published in a 20 impact factor journal, Nano Today. And we are still working with Professor Sujata of ICGB, so that these molecules can really help to combat COVID-19, because we don't have this biosafety 3 system and this COVID samples, so that we can treat the samples here. So we are trying, we are not stopping here. We are trying to collaborate, and we are doing the work so that some potential breakthrough can come in the near future. So another important thing, since I said that I was apprised about Click Chemistry by John Moses, so I thought, why not come back to India and do something novel work? So we developed a new monomer, and I take the privilege to acknowledge Dr. Debolina Rai. Dr. Debolina, please stand up. Dr. Debolina Rai, from whom I learned that, yes, because John Moses was there, but can we do something? So we did hours and hours of brainstorming session, and she's a alumni of IIT Kharagpur, and then moved abroad with a couple of postdocs, came back and serving as a assistant professor in biotechnology, and she's an adjunct professor also of our Amity Institute of Click Chemistry department, worked with me and with our student Aarti Singh, and made this happen. The new monomer we have developed with the help of Click Chemistry, and this monomer then is utilized to make free radical aqueous copolymerization to make the polymer, which was helpful to combat the diabetic wounds in 13 days. And this was published in European Polymer Journal. So we have published ACS Nano, Material Horizon, Green Chemistry, Nano Today, all as corresponding author from Amity. And you will be happy to know that our students have gone to University of Duke with 100% fellowship, because they have published this kind of papers as first, second, and third authors. To name few of them, Rohan Bhattacharya, Dakshi Melan to Carnegie Mellon University, then Piyush Garg to Waterloo University, and the recent one, 5 papers he has published in master degree, and he has gone to work in UC Berkeley with a renowned person, Omar Yagi, in the field of metal organic framework. So that is a huge success of Amity students, and a big round of applause for that. So moving on to the publications, these are few of the publications, 7 patents granted till now from my group. And now moving on to the next person, Dr. Saikat Datta, who has started working in the area of functional materials, electrochemistry, nanoscale, and he has started a lab, electrochemistry, energy and sensor laboratory. And it is very happy moment for Click Chemistry that he has been introduced in ACS as an editorial board member of ACS Sustainable Engineering, Environmental Science Advances, Interdisciplinary Medicine Journal of Willy. The pronged approaches of his research are material chemistry, nanoscale science, electrosorptions, supercapacitor, metal ion batteries, biosensing, mRNA detection and nutrient delivery in crops. And we have a couple of projects working in this area. He joined with us as a DBT Ramalinga Swamy Fellow, and he's ranked 2% scientist by Stanford University in 2021. This is the different electrochemical sensor laboratory glimpse of few of the instruments which he has purchased after coming from abroad with his Ramalinga Swamy Fellowship Fund, and tried to develop the electrochemical sensor laboratory. The current research, electrochemical energy, atomic scale materials, enzymatic biomaterials. The recent publications as corresponding authors, again in biosupercapacitor, exoskeleton, alloy for OER, single atom electronic engineering, enzyme-driven supercaps electrodes, heterostructure for OER, DFT analysis, and some of them were featured as front cover. So this is the graph of his publication status from 2019 to 22. And these are some of the cover page which he has done after joining Amity Institute of Click Chemistry. The second one, Molecular Materials and Research Laboratory, Dr. Ranjan Patra, whom I introduced to you in the morning, that after joining, he has published to ACS Catalysis. His pronged approach of research is supramolecular chemistry, bioinorganic chemistry, single molecule magnet, photoluminescence, polymorphism, catalysis, and computational modeling. And he was also awarded as an emerging investigator in crystal growth and design by American Chemical Society in 2019. And he got this award with the affiliation of Click Chemistry. So that is a pleasure moment for me as a director to tell in front of all of you. So these are the coordination chemistry, supramolecular chemistry, polymorphism, single molecule magnet, computational modeling, photoluminescence material. Publications from Click Chemistry, he has published in ACS Catalysis, twice, PCCP, Chemistry and ASEAN Journal, Crystal Engineering, Chemistry Select, Crystal Growth Design, Inorganic Chemica, and last year, I think he has published a very good work that has been featured in ACS, American Chemical Society, that is Inorganic Chemistry. Moving on to the third person, Dr. Vivek Mishra, who has 3 patents, 1 US patent and 2 Japanese patents. His area of research is organic synthesis, click chemistry and heterocyclic analogs. Green chemistry is one of the pronged approach, hydrogels and drug delivery, the another one, ionic liquids and aerogels, functionalized carbon dots, antimicrobial resistance, environmental remediation. This is the publication status from 2020. He has joined in 2020 till 2022. We are giving the publication status. And the current research is biomass generated functional CQD for antimicrobial resistance. He's trying to conjugate the click with the help of click chemistry, and he's making the carbon quantum dots receptor binding with the help of click chemistry. Biological applications of synthesized superabsorbent hybrid hydrogels, metal doped magnetic carbon aerosols for catalytic applications, heterocyclic analogs in silico and in vitro. He do care about the in silico work. Then the youngest chap in our group, Kambu Navitharan, who joined with us as an SRS award, and he works in the area of new synthetic organic methods via click chemistry, new copper catalyzed click sulfonyl azide cycloaddition reactions, and we have recently received a good amount of fund from DST in the area of suffix click chemistry. And the student Radhika Chaurasia has received that fund as a woman scientist, and I have been a mentor along with Dr. Kambu Navitharan. He has published 2 organic letters after joining Amity Institute of Click Chemistry, one in another in 2022, and now he's working with the Horizon Prize winner Hans Juelhof in Netherlands. Then came the 6th member of our team, that is Dr. Pooja Prasad. She's again a MS and PhD from IISc Bangalore, did a couple of good works in ACS Applied Materials and its interface, ACS Applied Polymer Materials, ACS Nanomaterials, and she is not only expert in materials, but small molecules development. She has also expanded her work in cancer biology, and I have given her the lead to take the cancer biology center for our Amity Institute of Click Chemistry. So can she do some work which Caroline Barthoji has done, and can she do some brainstorming and make up novel molecules that can combat cancer? So that is another approach. These are the research highlights and publications from her group. These are the publications from her. She has published recently with us Dalton Transaction and ChemCom. The youngest member and the true hardcore organic chemist who has joined recently, Dr. Milan Bera, and is very, very competitive to get Ramanujan Fellowship from abroad because they are limited seats. But I tell you, my dear friends and colleagues, Milan Bera has received this Ramanujan Fellowship because he has published Angwantha Chemi, JACS as corresponding authors, and a chemical name is launched, which I'm going to show in the next slides, with the name of Dr. Maiti, his mentor, and his name in Aldrich, which is a very big moment for us in click chemistry. And I hope that in the long run, he's going to have same different type of the molecules, and it will be again published in Aldrich, and it will be also commercialized by Indian market. So his area of research is photocatalysis and synthetic methodology lab, photocatalysis, transition metal catalysis, and drug discovery research. The selected publications are Angwantha Chemi, JACS, ACS Catalysis, Organic Letters, Trends in Chemistry, Journal of Molecular Catalysis, GOC, and notable contribution, which I said, that Maiti Bera Modok auxiliary that has come in Aldrich, and this is in the name of this name reagent. We are not only that the faculties are doing good work. Yes, we have a very good pool of staff, Mr. Mukesh Bhatnagar and Jayashree, who is an MBA academic coordinator, helping the students, working shoulder to shoulder and moving us ahead with that. We have self-motivated research scholars. We have a very good infrastructure and learning. We have developed molecular and material science research laboratory, biological and molecular science research laboratory, molecular energy and catalysis, and 3 more are coming. One is photocatalysis synthetic laboratory, animal cell culture laboratory, and electrochemical cell culture laboratory, cell laboratory that is being done by, that will be again leaded by Dr. Pooja, Dr. Milan Bera, and Dr. Saikat Datta. These are the infrastructure and learning. Again, the equipments which we have in our department. The department is small, but we have at this moment 5 crore. Just yesterday, it is around 6 crore within 6 years of establishment of our department, and the funding is received from Department of Biotechnology, DST, ICMR, and other funding institutes. The programs which we offer, Masters in Molecular Chemistry and PhD in Molecular Science and Engineering. We also give a foreign language for unique value addition to learning. The achievement of EICCR students, Rohan Bhattacharya went to Duke University, and from there he's working with he's working with Musa's lab, and Musa's received her degree with Donaling work in Weiss Institute. And so it is a very big opportunity for Rohan Bhattacharya to get and work with even Weiss Institute. And he's joining Boston after completion of his PhD with Musa's lab. Dakshi Kocha working in Carnegie Mellon University. Sampath Jibanananda working at Puhan University. All have received 100% scholarship. So we made it possible that it is not like that. It is only from IITs and other places or ISARs. We can do it if we have the environment and if we can build that type of system, and we can make it possible and we can make it happen. Some of the achievements, Aarti's work, we were the first group to develop, to find out a method for diabetic wound healing, and with a material which is a hydrogel nanotubes with ice helix, and we predicted the mechanism, how these ice helix were formed by the structured water, and that work was again featured in a very high impact journal, Material Horizon, and that was again featured by Science Chronicle and The Hindu. The achievements of our students, our master degree first batch, Arnav Chakravarti with 100% fellowship. She has gone to work with University of Miami. Simran Jindal went to work with Robert Langer student in Israel with 100% scholarship. Akanksha Agarwal, one of our students, has gone to work with Dr. Steed in the School of Medicine in Washington University. Ritesh Anand is working with Jubilant in biochemistry in Noida. Niharika started her own entrepreneurship in chemicals designing. So I'm not going into the slides in details. This is the first batch with our faculties. At that time, some faculties, Dr. Pooja and Dr. Milan Vera, were not there. Visit of eminent scientists at AICCRS for collaboration and beyond. Activities in AICCRS. And the last, no matter what you learn in life, the pedal keeps changing. Pedal hard and keep pedaling. So success is not a one-day job. It is performance, persistence, discipline, attitude, failures, patience, excel, determinations, risk, and hard work. And I should acknowledge our Honorable Founder President, sir. When God pushes somebody, inspires somebody, leads somebody, no power in the world can stop such person. This is our Founder President, Ashok K. Chauhan, and thank you. Sorry for taking more time. So now I request our distinguished guest to be here with us and listen all the talks of the morning. I think you will be energized with new molecules, smart molecules, how they are helping. Before we start that session, I would request Selvamurthy sir, the ASTI president and the main mentor of Amity University, to grace this occasion with his few words.
My dear students, distinguished faculties, we are privileged to have such a galaxy of eminent luminaries, scientists, achievers, and those who have committed and who have contributed immensely to chemistry, materials, and many other disciplines of science and technology. So let's welcome our distinguished guests. We are fortunate to have Professor Jayant Kumar, and he is the director of Center for Advanced Materials from the University of Massachusetts, which is not very far from our Long Island campus, which founder president, Dr. Ashok Chauhan, has created an Amity Global Research Hub in the Long Island's 100 hub. And founder president, he gives total focus for research innovation. For him, that's a junoon. And he will leave everything else and attend such functions. So I'm sure he will be listening to this program as well, because click chemistry is very close to his heart. And Mona Lisa, and being an achiever, and he holds her in high esteem. So let's clap for this Institute of Click Chemistry, which is doing a great job. All those faculties under the able leadership of Dr. Mona Lisa Mukherjee. Amity is blessed to have such distinguished people like Mona. She is now building a big team. You saw the profile of all those faculties who are here, the alumni who have passed out from this Amity Institute of Click Chemistry. They're all doing extremely well. So that is why I always say that a leader will churn out future leaders. So I see Dr. Mona Lisa, from the way she presented in such a short time. 6 years is not a big period for an institute to be built. And she has done it, and building people more than building equipments, research labs. It is the people who are important, and she has brought the best brains. So I'm very confident that these people and under her leadership will do a great job with our brilliant scholars sitting over there, PhD scholars, students who are in the Amity Institute of Click Chemistry. You are the future global citizens. We are preparing, Amity is preparing you with knowledge, including spiritual knowledge, skills, including soft skills, behavior, sanskars, values, resilience to face challenges. So that is why you will stand head and shoulders above all the students across the globe. So please remember that your responsibility is not going to be 1.4 billion people. You are going to make an impact, influence these 7 billion people across the globe. That's why equip yourself, prepare yourself to be that power, which is India today is. And Professor Jayant Kumar, I was just interacting with him, his interest and his immense contribution from this very distinguished University of Massachusetts. If you look at the world ranking, is in the top positions. So we are very fortunate to have him with us. Professor Amitabh Jha, head of chemistry department in the Acadia University in Canada. I was just having a brief chat with him. What are your interests? So he was telling the chemistry, these small molecules, natural products, and you learn from natural products and then you synthesize the synthetic molecule. So he was mentioning about the interest in phytochemistry and the chemical biology. So thank you so much that we will learn a lot from you. And we are also fortunate to have our own friend, Dr. Parmar, whom I have known, interacted, worked together, right my days from the DIPAS, Defense Institute of Physiology and Allied Sciences, where we were working on nitric oxide molecule for soldiers in high altitude who develop pulmonary edema in the lung. How do you treat them using this nitric oxide and oxygen in combination? So we cured many patients. Now that's a protocol of treatment. And I published this paper in Circulation, which is one of the high impact journal in this domain. And we should have published in New England Journal of Medicine. We just missed by a few weeks because there was another paper which came. So we had to publish in Circulation. So I have a long association with our Professor Parmar, who is also our honorary professor. He is honorary professor. I visited his university, CUNY, the City University of New York, where he took me there on a holiday, specially opened for me and brought the guests and also the chief of that division. Wonderful laboratory. So, and two of our students he is taking, he has facilitated from this group, Amity University. They are already full scholarship. He has facilitated that to happen. And he is also honorary professor, adjunct professor. He publishes papers with Amity affiliation. So thank you very much for being part of Amity's growth and development. Your contributions will be of immense value in future as well. And my compliments to Dr. Mona Lisa, Dr. Saikat Datta, Dr. Ranjan Patra, Dr. Vivek Mishra, Dr. Pooja Prasad, Dr. Miran Bera, and all those. Dr. Chakravarti, who is sitting here, who is the Deputy Director General for Amity Foundation for Science, Technology and Innovation Alliance. His group has facilitated to bring the best brains. That group founder has given a big mission, B4, bring best brilliant brains to Amity, bring best brilliant brains to Amity. So which he is involved, and all these fellows, Ramalinga Swami, Ramanujan fellows, inspired faculties, all this, his group, Dr. Chakravarti, let's give a big clap to Dr. Chakravarti and his group, and the SNT warriors, founder president called them science technology warriors. They work on mission mode. They work like soldiers in the battlefield. So that is why this name SNT War Room and SNT Warriors. Thank you, Dr. Chakravarti. And now coming to the topic, which all of them are going to share with you, the seminar topic is very, very important. Topic is molecular chemistry and smart materials. See, chemistry is there across every field. The life is full of, the life itself is chemistry. When you look at the biosphere, it is chemistry. It could be organic chemistry, inorganic chemistry, biochemistry. Now Mona Lisa has coined a very important term and started a course here, molecular chemistry. See, biochemistry, everybody knows. But she started first time here in Amity, that molecular chemistry, and she has started a master's program in molecular chemistry, bachelor's in molecular science and engineering. Because we look at the man physiology, biochemistry, psychology, at the human level. But then she is now looking at man to molecule. then you understand many things much better. So your intervention, health, everything will be biotechnology. You will get a great leads. So that is why this conference, this seminar on molecular chemistry is going to be a very important. Then the other important component is materials. Materials are the building block for everything, whether it is a system of systems, components, devices, everything is made of materials. So that is why these two, molecular chemistry and materials, engineering materials, is very important. Smart material, that to smart materials, because you have many materials, but then she has focused on smart materials, functional materials. And so the topic is going to deal with smart materials, because when I was at DRDO, materials is very important. We have a separate materials division in Defense Research and Development Organization, because we have to build the exotic materials. It could be of strategic importance, high energy materials. And we need storage, energy storage materials like batteries. So we work on materials, metallurgy. We have a very strong group in metallurgy. So all this is in DRDO itself. I have given a big we have given a big focus on smart materials. We started a national program on smart materials, NPSM, which Dr. Atre, the scientific advisor, headed at that time. So we have done a part of that as a part of the mission in NPSM. And we did a lot of MEMS was the focus, MEMS as a new materials. And we did a lot of new materials came from that study. And the program, it was not a project, it's a big program, national program. We also developed shape memory alloys, and we developed high temperature materials which can withstand missiles when it takes off. You imagine the plume which comes out of it. You need anti-ablative materials, very high temperature tolerant materials. Similar thing in space. So you need those materials which can withstand the cosmic radiation when it goes through the space. So these are all very vital. Smart materials and advanced materials is very important. Then now quantum materials is the latest, which is now coming in, is quantum materials, quantum technologies in which quantum communication, quantum computing. But now in materials, quantum materials is coming in a big way. Then spintronics materials can be packaged a large number of memory into small space with less energy. Spintronics materials. So when I talk about smart materials, advanced materials, you can go on expanding. So Mona Lisa has really picked up this very important area. But like a drug development, new material development takes a long time. So sometimes 10 to 15 years, like when we develop advanced materials, right from the concept to realizing, getting into production, it's almost 10 to 15 years for a new material. But how do you reduce this? Now it is possible with data science, artificial intelligence. You will be able to bring advanced materials, smart materials much faster. This group, our group in Amity is really looking at those opportunities. Our students are taught even such kind of application of artificial intelligence and data science in the new material development, including smart material. Then we are also having industry connect, because ultimately after materials come in the laboratory, how do you upscale it? How do you give it to the people? So we are also looking at materials engineering, and also ultimately the industry has to produce them. Now, thank you so much. This conference, Mona, you have chosen a very important topic, and all the three people are going to deliberate. But now a little bit about Amity Group for those people. Today, Dr. Ashok Chauhan has created a universe, Amity Universe, with 12 universities in India, 18 campuses abroad, 28 schools, 200,000 students, 700,000 alumni across the globe. It's a big universe. And this focus is on research and innovation. We have filed 1,900 patents, and we have also published 40,000 research papers in journals of repute. Our university H index is now 126, but it's moving towards 140 very soon. So this is all in such a short time of about 18 years. We became university in 2005. So in 18 years, all this is possible because of the committed faculties, brilliant students, above all, the drive engine, which is founder president, the chancellor, Dr. Atul Chauhan, product of London School of Economics, the Vice Chancellor, Balvinder Shukla, and all this together, and the ecosystem, the missions which drive this, mission outcome, mission synergy, synergy with you people. So this is how is the secret of Amity growing at this exponential rate. And then we also have institutes like Amity Institute of Click Chemistry, Amity Institute of Nanotechnology, where there are many nanomaterials, polymer composites, and we work on nanocomposites. So we have Amity Institute of Nanotechnology. We have Amity Institute of the Advanced Research and Materials and Devices. Dr. V.K. Jain heads that. So they bring new materials. And also hydrogel. She mentioned about nano hydrogel. Polymers, ceramics. We have Amity University here got tremendous strength in ceramics and spintronics. So these are our inherent strength, but we would expect the people who are sitting on the dais, Dr. Singh also here, Dr. B.K. Singh, he has also joined us from CUNY. So thank you so much that we want to work with you. See, ultimately, whatever Amity, what I said, because of you people, the synergy coming from such great institution, our partners, there are almost 200 partners across the globe who have formal MOU. We have MOU with ICMR, ICAR, CSIR, DRDO. So this has helped to growth. That is why it's a force multiplier. So I look forward from your institution, not only you, but your institution to build a synergy, because founder president again has started a mission synergy, mission outcome. Mona, we will be waiting for the outcome. What will be the sustainable outcome from the deliberation? That they are spending their time here. So many brains are sitting here spending their time. So we would be expecting a fruitful, sustainable outcome from the deliberation. And let's give a big clap to our students, because these are the ones who will transform the world. So you are brilliant, and best wishes, blessings to you. And also thanks to all the people, faculties who have organized this event, and have a wonderful, this fruitful event. Listen to every word of the presentation which will be made by these experts, but they're all repository of treasure house of knowledge, experience, expertise. Listen, harness that. Best wishes.
Thank you, Dr. Selvamurthy sir, for such an inspiring talk. Now I request Dr. Selvamurthy sir and Professor Mukherjee for felicitation, right? For the felicitation. So please come. And also, Chakravarti sir, Dr. Chakravarti sir, please come on the stage for felicitation. Jai Kumar. So first, I will request Professor Mukherjee and Selvamurthy sir to felicitate Dr. Jayant Kumar. Yes, please, a big round of applause for them. Thank you, Chakravarti sir, Selvamurthy sir, for felicitating him. Now, yes, there are some more. Thank you. Now, now I request Professor Amitabh Jha, please come on the stage here. Now I request Selvamurthy sir, Dr. Chakravarti sir to felicitate Professor Amitabh Jha.
A big round of applause. We request Dr. Shoikat Datta, Dr. Ranjan Patra, Dr. Vivek Mishra, Dr. Milan Bera to come on the stage, and please, Dr. Shruti, Dr. Devilina Ray, please. Oh, now I request Professor Singh to come for the felicitation. Yeah, thank Sir, Sir Selvamoorthy sir, Dr. Deepshika ma'am, she's Dr. Kiran, yeah, thank you for coming. Come. Now I request Dr. Sharma to please come for the felicitation. Yeah, a big round of applause. Now, our guest of honor, now Dr. Parmar. Yes, sir, but it will be honor for us. A big round of applause, please. Thank you, Dr. Selvamoorthy sir, Dr. Chakrabarti sir, for your felicitation.
So the first speaker for today's morning is Dr. Jayant Kumar. So I'd request Dr. Saikat Datta to introduce him. Yeah, please. I have tried to keep the faculties to introduce the respective guest, honorable guest, in the way that their research area matches their research area of the guest. So in that way, Dr. Saikat Datta do a lot of work in nanomaterials, 2D materials, electrochemical sensor, and chemical engineering. So I thought, who can be the other person to introduce our honorable guest, Dr. Jayant Kumar.
Thank you, Professor Mona Lisa. So I welcome all for the first technical session of this international symposium, where we have our distinguished speaker as the first speaker to inaugurate our program. We have Professor Jayant Kumar from University of Massachusetts Lowell, who is there as director at the Center of Advanced Material, which is in the Department of Chemistry and Physics. Professor Jayant Kumar has been known in the area of material physics and chemistry for many years, for many decades. His record says all that how he has achieved a distinguished stature in the area of material physics and chemistry. Professor Jayant Kumar started his career from India, Indian Institute of Technology, Kharagpur, where he has completed his PSMS and then moved to United States for PhD. He did his PhD from Rutgers University. And then he started his career in the University of Massachusetts Lowell, where he has worked in many areas of material physics and chemistry. I will just name a few from a long list. His group is interested in the area of material science, optics, and electronic properties, optical spectroscopy, integrated optics, optical spectroscopy of nonlinear materials, dielectric behavior of materials, and so on, which also includes nanoscale materials and novel polymeric materials. I will just name a few awards from a long list of awards and honors that he has received from the United States. Few of them are, for example, the awards on People, Prosperity, and Planet from US Environmental Protection Agency. Then more number of awards from US Environmental Protection Agency, for example, US Environmental Protection Agency Award, and US Environmental Protection Agency Award repeatedly from 2006 to 2011. Then Excellent Research Citation Award, Outstanding Graduate Advisor from Leadership Award, US Environmental Protection Award again from in 2011. There are Outstanding Graduate Faculty Award he has received from University of Massachusetts Lowell. So I just name a few from the long list. Today, Professor Jayant Kumar is going to speak on molecular and polymeric photovoltaic materials and devices and their associated challenges for commercialization. With this, I would like to invite Professor Jayant Kumar for his talk. Thank you.
Thank you very much for your very kind introduction. And I'd also like to thank Dr. Mona Lisa Chatterjee and of course, Dr. Salvamurthy and all of you for inviting me, whoever was involved, but also it's been a great privilege for me. This is my first visit here. And I'm just, I would say, amazed at the amount of energy and enthusiasm and a lot of research work which is being done here. So without much ado, I will, basically share with you. Actually, this area sort of, we've been in it for a long time, starting from mid-90s. But, and of course, it has gone through different cycles. And we, when I say we, it was a very good friend and colleague of mine, Sukant Tripathi. And together we started the Center for Advanced Materials in 1992. I went to UMass Lowell from University of Southern California, where I was in the electrical engineering department. I was working on nonlinear optics. And the idea was, okay, he kind of persuaded me because you need a lot of persuasion to move from University of Southern California to UMass Lowell, because you don't have the winters there, the weather is nice, and so on, and the university is pretty good too. So, so the whole idea was, okay, he was a polymer scientist. And let's look at optical and electronic properties of polymers. That was initially what we started on, and that's what we worked on nonlinear optics of polymers. And of course, I'll let you on in another. I mean, I guess here among the speakers, I'm the only non-chemist. But actually, and our dean and actually the provost once told me that a lot of people confuse that you're in the chemistry. And I said, that's a great honor for me, you know. Some physicists, you know, they have a kind of a rather snobbish opinion, you know, they're the chemists. But basically, I have really enjoyed this journey and this journey into material science. So basically, to begin, and what you find is, if there is a take-home message, basically any practical problem actually requires a lot of different disciplines to come together to solve anything. Okay? And it's very so this area has you know, my training is in physics and optics, but there were, you know, chemists who made materials, the device physics, and so on. So you need a lot of inputs. So most of you, of course, I don't need to tell you about photovoltaic technologies, you know, with all this buzz about climate change and all that and renewable energy, this has been all over. So of course, the ones which we see most often are, you know, crystalline silicon on glass, you know, these kind of solar cells. Then there have been solar cells which are basically thin film solar cells. And a lot of these are also in glass, amorphous silicon being one of them. Then, you know, more recently, thin films, CAD telluride based solar cells, not very recent, but more than 20 years ago, and it's been commercialized. And now, actually, in the last 25 years, as I said, we got into this area 25 years ago. I mean, we were not the first. Actually, you might have heard, you know, dye-sensitized solar cells. And Michael Grätzel, what got me very interested in this area was there's a paper published from EPFL in Switzerland, where Michael Grätzel basically published that he absorbed certain dyes, these were ruthenium dyes. And then using a redox couple, you know, he made a solar cell and he could get, you know, 9 to 10% efficiency. And that really wowed me. And so I then went along, talked to Sukant and said, well, you know, this looks like a very interesting area. So of course, we got into polymers and nanomaterials. And what you see here is, we published actually the first paper using a P3HT. Of course, it was a regio-random P3HT, poly-3-hexyl thiophene, which is a polymer, thiophene-based conjugated polymer. Basically, so we published in 95, 96 timeframe. The efficiencies were pathetic. They were terrible. Something like 20% or something, you know. But of course, in those days, you could not, you know, we didn't, perhaps we were not very good at synthetic chemistry because we just used C60, you know, the fullerene, and a regio-random version of poly-3-hexyl thiophene. So, you know, to make it regio-regular, that means having head-to-tail coupling, most of it, you have to use more complicated chemistry, which was around, but of course, both Sukant and I actually, I'll let you another secret, Sukant was not a chemist either. You know. So he was a physicist who did a PhD in computational polymers. So basically, we made those solar cells, but actually by end of 2000, these things were commercially available. And there was a paper published which reported that using regular poly-3-hexylthiopene, and the efficiencies were like, 2%. At that point, we also did a lot of research. We got some patents, and we spun out a company whose name was Konarka Technology. And this came, unfortunately, in 2000, Sukant passed away. And that kind of, delayed this a little bit. It was really sad because he was very enthusiastic about it. And so in 2001, this company, Konarka Technologies, came about. And what you see here, for instance, let me show you that. Oh, okay. So over here, these are actually solar cells made out of poly-3-hexylthiopene, PCBM, and then an interface layer. And these have been made on flexible substrates. The other thing is, when we do research, a lot of times between what is commercializable and what will publish are two different things. For instance, for commercializable, something commercializable, I mean, a lot of things are very important. It should be scalable. It should be stable. The cost should be reasonable. If you want to publish something, then of course, I mean, basically, even if the solar cell is 1 millimeter by 1 millimeter, which is thoroughly useless as far as practical applications go, you can probably get it in a high impact journal. So question is, what is it you want to do? Okay. So you'll see a lot of papers which have come out in science, which very high efficiency, but the solar cells are very small dimensions. So, we've done that. And of course, in 2011-12, this perovskite, which is, perovskite is actually a certain crystal structure, but these are, organic, inorganic perovskites, which have shown a lot of efficiency. So before we started the company, this was basically one of the solar cells which is driving a fan. And of course, we had to give this demonstration because it was a venture capital funded company, Konarka. And of course, they like to see these things. So, I'm not going to spend much time on this. So basically let's consider the main things required for high efficiency. So you want a solar cell, which ultimately, hopefully will get commercialized. So you want reasonably high efficiency. And so to get high efficiency, what do you want? You want efficient light harvest, okay? Which means the LUMO-HOMO of these materials, whether they are small molecules or polymers, I mean, they should nicely cover the spectrum which the sun puts out. That's roughly between 400,000 nanometers, and silicon does this very, very well. But organic materials don't easily oblige. So, a lot of synthesis, especially, good synthetic expertise is needed. Then, of course, you absorb light, you generate electrons and holes. You don't want them to recombine and either emit light or just generate heat. So you want them, so you want charge generation to occur, charge separation, the electrons and holes. And basically, so you need to engineer that in by appropriate electronic energies of interface materials and the harvesting material. And finally, of course, there's charge transport to the electrodes. So the materials you use cannot cause a traffic jam of the carriers, okay? So you need what is called good carrier mobility. Okay, so all these things are important for high efficiency. So for instance, conjugated polymers are, say, these P3HT is an example. It doesn't give very high efficiencies. Polymers with much higher efficiencies have been synthesized. But you have the conjugated polymers, they have reasonable, hole mobility. But unless most of them, like P3HT, have terrible electron mobility. So that won't do. Because again, I mean, your holes can move, but the electrons get stuck. And finally, basically charges won't move because, that layer will get charged. So basically, you need to optimize things, for instance, make sure that, you have good solubility. If you want to do solution processing, uh, have the right LUMO homo structure, and basically, also these materials a lot of times. So for instance, we use P3HT PCBM. The problem is they tend to diffuse and aggregate, and that basically causes problem. So in this P3HT PCBM system, you see, P3HT is a terrible electron transporting material, as I told you. It will transport holes well. So you need a phase separated system like, shown in the middle here. Let me, okay, this one here. So that electrons basically move through PCBM, which is a reasonably good electron transporter. PCBM is this molecule which you see here. And the holes move through this poly-3-hexyl hierarchy, which has decent hole mobility. And in that case, you can extract the charge. You can have a single layer system, but then, of course, what happens is this doesn't work well because there's only one interface where you can separate the charge. Here, there are a number of interfaces. So this is called a bulk heterojunction, basically, configuration. People have tried various other things, all right? So most of for Konarka, we really tried this bulk heterojunction system. So now if you want to commercialize these, photovoltaic devices, which are either molecular or polymeric, and not just, get a paper out either, in a high impact journal. One of the things you have to worry about is the stability of the active component. So of course, a lot of these molecular materials, they actually have stability issues because of photo decomposition. So, you have to worry about that. Also, you have these interface layers, which, as I told you, to extract the charges, we need certain interface layers. And actually, they can delaminate because any solar cell or PV device basically cycles through a range of temperatures. For instance, if you put it out in the sun, the temperature can go up to 65 degrees, or something, and then at night it falls. So you get this, expansion, contraction, and these interfaces can delaminate, and that's the end of the device. You have to worry about all these things due to environmental factors, could be due to photo degradation. Then, of course, if you want the PV's device system, you want typically to make a module, not just one single solar cell, you have to scale it up because finally, I mean, you want to connect many of them to get the voltage you want, the current you want. And for that, scalability is very important. And what you saw earlier was, this, I'll show you some pictures later, how with Konarka, one tried to scale it up, and so if you make solar cells by hand, one at a time, actually, it probably, if you get a module working, it'll be so expensive that, basically, people will stick with silicon. So that's one of the issues, scalability and mitigation of device degradation. Again, all solar cells, including silicon, they basically have barrier layer because, you have electrodes. If the electrodes corrode outside, so you have rain, you have, probably which moisture can get in, it can corrode the electrode. That again will basically kill the device. Yeah. So basically, sealing these devices appropriately, that actually is very important, you know, by using barrier layer. So let me just, yeah. So just to tell you how these devices work, okay, so one of the things in all these any solar cell, and for that matter, especially these molecular or polymeric devices, is basically you know, how the energetics of the materials come about. So you have to choose materials, HOMO and LUMO levels, for instance. So here, where is the pointer? Is there okay. So here is P3HT, poly-3-hexylthiophene. It is like a semiconducting polymer. You know, it basically absorbs all the way to something like 650 nanometers. So when it absorbs light, it makes this transition here. And then, of course, the electron basically is grabbed by PCBM, which is a very strong electron acceptor. So you separate the charges, and that happens very fast. This photo-induced charge transfer into PCBM occurs at, you know, something of the order of 100 femtosecond times. So you have separated the charges in this case, and the back reaction rate is more than an order of magnitude, you know, slower. So you separate the charges efficiently, but as I said, now the charges have to, you know, diffuse to the way. And so basically, that's why the PCBM is a good electron transporter, and it grabs the electron. The hole left in P3HT then basically diffuses through it. That's a decent hole transporter. And finally, the energy levels should be so configured that actually there is no energy barrier in basically the way the electrons move. So, you know, they make a transition from P3HT LUMO to the LUMO of PCBM, which is empty. And so those states are available. Those states are available, and then they're collected by basically the aluminum electrode. And the holes get collected by, you know, PDOT. PDOT is a conducting polymer, and that forms a good interface with P3HT. And finally, the holes, you know, float up. The electrons typically come down. Oh, great! Thank you. So this pointer works. Oh. Okay. So what? Can somebody? Okay, let me just. Say okay here. Okay, so okay, so to move it up and down is this. Oh, okay. Okay, that. Thank you. Okay. Okay. So, you know, the energy levels is very important that the energetics are right. Then, of course, we have to do other things like we have to measure the mobility, make sure the mobility is decent. This is just an example of mobility measurement. for instance, in P3HD. And I won't go into the details how we do that. This is a technique called time of flight, which we use. There are other techniques also. So as far as synthesis, because there's a lot of chemistry interest here. We have synthesized some electron transporting conjugated polymers. This is work done in collaboration with Professor D. Venkatraman from UMass Amherst. And of course, we did not use this as an interface layer because the solubility in this case was very poor. So you see how many parameters you have to optimize. That's the big problem. This was another work which we did with UMass Amherst. This is Professor Paul Latti and Thayu Manovan. And they synthesized this additive to P3HD, which is called scorenes, these kind of materials. And when you put them as additives, then you can increase the efficiency, as you see. So, all these games we have played over the years. And in this case, the efficiency is not very impressive. It's like, you get it up to 4.6%. But this is just the journey I'm showing, we've been through over the learning curve over the last, I would say, 12, 13 years. So, there is a threat between the scorene and the P3HD, et cetera, which enhances the efficiency. For instance, you'll see here P3HD, basically just over here, it peters out, it kind of dies with efficiency because it doesn't absorb much there. When you put the scorene, then actually you get this added at a high, contribution to the photo-induced current efficiency at longer wavelengths. So this is just for fun. This was a dye which is indanthrone. This is used to actually, you might see this as the color of the genes. This is used to color genes. This dye, the sulfonated version of this, which is soluble. So this dye, which actually is like brick dust, it doesn't dissolve anything, but we evaporated it, we made a solar cell, we measured its, mobility, everything. And actually, what the good thing about this, oh gosh. Oh, I got it. Okay. So the good thing about this is, so this is just a whole mobility measurement. You basically these show the absorption spectra, etc. But when you do the efficiency just for a single layer device, you can get 2%. And the interesting thing about this is this dye, indanthrone, is really a tough dye. You can put it out in the sun. It doesn't bleach much, So P3HD, if you put it out in the sun, actually degrades. So this is the photo conversion efficiency, 2.5%, which is kind of low, but this was actually a fun project. Also, as I told you, if you put PCBM as shown here, these actually, especially the temperature goes up, they tend to diffuse and they aggregate, and that again kills the device. So you can play tricks like you can actually cause a dimerization that reduces the diffusion coefficient a lot, and then basically so these are just some studies on pristine film, and after dimerization, what happens to the absorption, etc. And what you see is the stability of the dye, once you dimerize it using a IR laser, using 2-photon absorption, it increases a lot. Again, the efficiencies, I'm not focusing on the efficiencies here because the efficiencies, we just want to first see whether we can stabilize it. Typically, a P3HD cell will give you 2 to 3% efficiency. It can't do better than that. I'll just skip over this because this is, so of course, talking about synthesis of materials. So this is work not done by us. People have synthesized all kinds of oligomers and polymers. And in this case, this is again, these conjugated materials, they're made tandem solar cells. That means you have one kind of absorber over here, all right? And then basically another kind of absorber over here. So you cover a wider spectrum. And then the efficiencies here can be much higher. You can get 17% efficiency in this case, okay? So these are some of the characteristics. I'll just skip these in interest of time. So this is another tandem solar cell, which, you know, uses this material here, these two different materials, and you can actually make it absorb all the way to 800 nano. Individually, you know, they have absorptions up. One of them has absorption around here, another one has absorption here. So it's the usual thing. How do you get the efficiency up? How do you get the stability up? How do you make it more scalable? Over the last 10 years, we've also worked in perovskites. These are actually organic, inorganic hybrids. So they use something, one which is most commonly used is what is shown here, which is called methyl ammonium lead iodide. You could also have lead iodide chloride, bromide, etc. People have played around a lot with this. These are very easy to make. As I often joke, you know, even I can make this, not, you know, not being trained as a chemist. And actually, and efficiencies of the order of 25% today have been reported on these, which is actually pretty much getting close to silicon efficiency. But the challenge is, again, as I said, you know, so people publish papers, okay, we got 20%, 22%. I and some of my collaborators and I also have reported 22%. But there are still problems, you know, it's very sensitive to moisture, okay? Basically, when it solar cell works, it gets a potential difference. So there's an electric field inside the material, and that causes migration of ions. So these perovskites basically have ions. They have lead ions. They have methyl ammonium iodide. So that there are ions, and in selective field, people have seen that basically these things change. So you can play around with a lot of these, you know, instead of methyl ammonium, you can have methyl diammonium, you can have formidinium and, you know, guadinium and all these things. So all these games, so this is where the synthetic chemist comes, and we had one from Korea, Youngju Bae, who synthesized a lot of these things. And basically, you know, played around with it. So here, basically, what you see is typical device size. Now, these are, as you know, few centimeters, maybe a centimeter long and a few millimeters wide. Now, for a practical solar cell, so while we've done work like this and even published it, for a practical solar cell, if you want to commercialize, this is a no-go. It just won't happen, you know, because actually the number of solar cells you have to harness together will just makes it not practical. The solar cell sizes have to be at least a centimeter. So this is and of course, to make them more stable, we also have played tricks by, you know, putting passivating these films and so on. So there are, just to get so I guess, how much time do I have? 5 minutes? So something which we have done very recently is, you know, perovskite solar cells usually use these, you know, triarylamine type of cold transporting layers, and many of them are doped. And what happens is this doped materials, they tend to be unstable. As you see, with time, actually, these things tend to decay. And if you go more than 50, this is let's see, 50 days or something, this will fall even more. So that's no good for a solar cell. This shows you the instability for it. This one is better if we take Omedad, which is another molecule similar, you see it dies very quickly, and that is doped with actually a lithium salt. So to try and address these, basically, so we made these kind of solar cells. These are formidarium ones, for instance, here, and so you use different interface layers, and you get all these characteristics which are IPC, which is the number of carriers generated per photon absorbed. Okay, and so just to cut the long story short, we synthesized this material. This was actually in 2020 roughly, and this is a fluorinated small molecule. It's also a whole transporting material. We have to do all the characterization. First, by using density functional theory, you can get an idea about the HOMO, LUMO, and the gap. But then cyclic voltammetry is what we use to get the HOMO, LUMO, and then we compare it with the UV, UV absorption. That gives us also the gap. So basically, we made a solar cell out of this. Just to cut a long story short, again, you'll see a lot of those curves, IV characteristics and so on. Basically, the efficiency here is 14%. And the stability, which, the decay is over something like 20, 30 days was almost, not measurable. So because of this fluorination, water absorption doesn't occur, and perovskite is very, very sensitive to moisture. So all these issues basically play into it. So it's a multi-parameter optimization, and that's what makes it such a challenging task. We have played around with other things. We have made X-ray detectors, for instance, with this perovskite, because it contains lead, and so lead basically has a very good absorption for X-rays, and so you can. This work is actually with people at Harvard Medical School who wanted conformal, X-ray detectors, and it's published, as you see, in Physics and Medicine. So we try to have fun, as much as we can. Of course, also try to do something which is practical. At the same time, of course, some basic science is also there. This is just to show you. This was actually, I showed you some of these polymeric, these flexible solar cells. These were manufactured in facilities of Konarka, Konarka Technologies. And actually, this is actually a coating plant. So you really need to scale it up. So if you want to impact a real problem, you just can't make it by hand. And here I have a 5 millimeter by 5 millimeter solar cell, and it's 20% efficient. Basically, that goes nowhere, because if you're going to make solar cells, on a large scale by hand, you will never, be competitive with silicon. You might as well stick with silicon in that case. So with that, this is a summary. There's been significant progress in photovoltaics, especially of the molecular and polymeric type. Not that it's ready for prime time. It's not. I mean, there's still a lot of issues with commercialization. Efficiencies in polymer-based solar cells are up to 15%. I told you initially with P3HT we were getting about 3%. These have come up to 15% with basically tandem cells. Again, tandem cells looks very attractive, but as you see, you have to make two different solar cells and connect them, and the complication actually makes it very difficult to commercialize it. Perovskite solar cells have shown very high efficiency, competitive with silicon, 25%. But basically stability is still a issue. Again, it should be scalable. If you're going to make it in the hand by spin coating and, so on, that's not going to fly commercially. So you have to be able to coat it on the kind of coating lines like I showed you, which, Konarka tried to do. Currently, several companies, but two which I'm familiar with. One is Oxford PV. This is a spin out from Oxford University, which is trying to commercialize perovskite solar cells. This company, I put it because this is from a former student. Professor Parmar probably knows him, Chitty Babu. So he founded this company, Ambient Photonics. This actually is not for full sun. So basically, this is a niche application, and actually they've raised a lot of funding, $30 million. Okay, and a lot of it has been funded by Amazon, because Amazon has these huge warehouses, and they want to interrogate what inventory they have. And so the warehouses typically have lights of this kind. And so for low light, and it'll provide power, and by RFID means, they want to interrogate them. So, and actually this can be even done. There are a lot of, I don't know whether any of you have seen on any documentaries or something, some of these warehouses of Amazon, a lot of them are full of robotics, these things. And so it can be easily integrated if basically that information can be fed to the, robots. They can go there, do whatever they have to do. They don't get tired like human beings, loading things. So basically that's where we are. So commercialization is much more difficult, in my opinion, than publishing. Okay, and so we've had papers in fairly high impact journals, but still, while you get a good paper with a good impact journal, it's really not going to impact, the world as such, because okay, it might be some interesting synthesis there, some nice, interesting properties like mobility and so on, but, and I'm not saying that that's not worth doing, but commercialization, as I have found out, from Konarka, which, by the way, Konarka has gone bankrupt, started in 2001. All right, it went bankrupt in 2013. It had, in its heyday, it had about 80 employees, okay, about 40 or 50 in Lowell, and another 20 or 30 in Germany. Okay, so of course, from its ashes, other companies, there's a French company which is trying to do something very similar, have come out. So it was not a total waste. There was a fair amount of money put in. I won't tell you, it's, I mean, it's way more than $30–40 million. So, it takes a lot to commercialize something. Just by looking at those facilities, you must have seen, they must have cost a lot. So with that, I want to end. If you have any questions, I'm sorry, I might have run over, but I just thought I wasn't quite sure how much time I had, 30 to 35 minutes. But I might have. So if you have any questions, I'd be happy to address them, or we can talk about it later. Yeah.
Good morning, sir. It's a very nice presentation. I want to ask about that. You have talked about perovskite structure. So basically, perovskite structures are like, if you molybdenum based or tungsten based, that is a like crystal structure to create that vacancy site in that crystal lattice. So how much it is challenging, because that perovskite structure is like one core structure. If you try to create some vacancy defect inside that lattice, so it can disrupt whole the structure. So
Yeah, so basically, absolutely, there are defects, which basically, and there are defects, they trap charges. And so, there was a slide which I just glossed over, which talked about passivation of these defects. So people have tried various methods to try and passivate those defects so that they don't become, big traps for these charges. So, you absorb light, you create electrons and holes, right? And they diffuse to the various electrons. But if you have a lot of traps, they get, they won't get there. And so efficiency will be impacted. So what that results in, that basically, so there are also a lot of grain boundaries. So these are all polycrystalline material. Okay, so when they're deposited as of now by either, doctor blading or spin coating or something like that. So they're polycrystalline, and you have also grain boundaries. And grain boundaries also act as, traps for charge. So that's why people use, they put different molecules to make sure that those defects do not end up trapping a lot of charge.
So one more question, that where you have shown that DFT means energy gap of HOMO-LUMO and hydrophobicity.
Yeah. So the hydrophobicity people have, okay. So
Means my question is, sir,
when you generate electron and holes in this perovskite film, okay, then finally you have these interface layers, which basically makes it easier for the charges to be collected by the electrons. Okay, so typically you have so because you don't want the device to short, you have typically one electron transporting layer and a hole blocking layer. And this layer is basically, just the opposite. It'll be a hole transporting electron blocking layer. So one is, electron transporting hole blocking. The other is, hole transporting electron block. So these two layers sandwich the perovskite, so that actually, the charges don't go to the wrong electrode. So, but people have mainly, a lot of people have used OMETAD or they've used P.PSS. Now, these basically absorb moisture, and moisture basically typically kills the perovskite, because I mean, it's a salt. It basically, in fact, degrades and forms lead iodide, which is one of the constituents of it when you make this lead perovskite. So, so basically, to passivate it, people put hydrophobic layers even in the perovskite film sometimes, and certainly you have to put it. What we have done is we have put a fluorinated material in basically the whole transporting layer. Okay.
so,
The electron transporting layer is just TiO2.
so basically, by making that hydrophobicity, that gap, HOMO-LUMO gap, it decreases energy gap.
Okay, so basically, of course, when you fluorinate something, its HOMO-LUMO will change. Because you're putting a fluorine there, which is strongly electron withdrawing. So that's why we if you look at this here, let's go back to it. Okay. So first what we do is, okay, you're going to make this. What we do is we get a rough idea by using density functional theory as to where the HOMO-LUMO will be. Okay. That's just the computer gives you that. That's not the last word. The last word is the experimentally obtained value. Okay, so all right, maybe in the right ballpark. So then what we do, once you synthesize, you basically do a CV, cyclic voltammetry. And from there, actually, you can actually calculate, what these levels are, and you can get a band. And then, of course, when you do the UV, so you have an onset somewhere over here, right? From there, you can calculate what the gap between the HOMO and LUMO will be. And you can see this is very close to 400 nanometers. So it's got to be experimentally, this gap between, HOMO and LUMO comes out to be roughly 3 electron volts.
Yes, and one last question, sir, that you have worked on solar cells on various materials like on glass substrate and other materials like textile based substrate. So what means you have worked on solar cells, so on various materials, substrates like glass substrate and textile based substrates. So what is the best performance you have got till now? Means what is the best substrate for?
For this one, the substrate is basically, this is ITO coated glass. For this particular. Perovskite, we have done on plastics, okay? In fact, there was data that I had to go very fast because I guess getting into the details of those, I think there's something over here. Maybe I've taken that out. Okay. So we have made perovskite solar cells on plastic substrate. So ITO coated, say PET, polyethylene terephthalate. And of course, the efficiencies there are lower. The reason being that those films are, plastic, you cannot get that good surface smoothness and so on.
So is this plastic surface is flexible or?
It's like what I told you right in the beginning. Of course, if you can get a flexible solar cell with high efficiency, I mean, people would be very impressed. Okay, which can conform to, shapes of buildings and whatnot, but that's not an easy thing to do. You might have seen it. So that's what, that's what Konarka tried to do. This is on plastic substrate here. What you see here, this was manufactured by this company, Konarka. We had spun off. So these are just done on coating line. And so these are actually on a plastic substrate.
Okay, sir. Thanks.
Thank you. Thank you for your attention.
Good afternoon, sir. Myself Rahul from MIT Institute of Click Chemistry. I have a couple of questions. I have a couple of questions. First, which parameter needs to be identified to reduce the band gap? Because all materials are not having low band gap, which are active for solar cell kind of device. Like I am working on porous carbon materials, their band gaps are very high. So which parameters one can think about to develop a material for solar cell device? That is my first question. Second is in perovskite, the common formula is AbO3. So during the synthesis, how to maintain that ratio? Because sometimes one can form a spinel type. So how to calculate and retain that formula during the synthesis procedure?
Well, okay, so you see, I mean, the P3HT, etc. Okay, for perovskite, in fact, when the first papers were published, which was first paper was from Japan, I think 2009 or something like that. Actually, we missed that paper. Finally, there was a paper which came out in 2013, and 2014 is when we got into it. So we initially tried this methyl ammonium lead iodide. Okay, the band gap of that was, well, had been, the UV base had been measured, so people knew what the band gap was. it basically, you know, goes up to about 850 nanometers. All right. So 850 nanometers in terms of the energy range coverage for solar radiation is pretty good. For instance, gallium arsenide, which forms very good solar cells and has very good mobility, basically has a band gap in that neighborhood. So we've just gone along with that. If you change, for instance, things like if you, instead of iodide, you put bromide, you can do that, okay? Then the band gap shifts. Or if you instead of methyl ammonium, you put something else like formaldinium, then the band gap slightly shifts, okay? So you want to make sure, if you want good efficiency, to have maximum overlap with the solar spectrum, right? But solar spectrum is a continuous spectrum, right? So essentially, you want to cover where most of the sun's energy comes out, which is, you know, roughly 800 to 900 nanometers. You intercept most of sun's energy. The IR part you don't get, the UV part you don't get, okay? But there, the relative fraction of energy which resides compared to the total energy which the sun puts out is not that high. If you take very low band gap, then you have a problem, because actually you cannot have a open circuit voltage more than the band gap. So so your what is called the open circuit voltage of the solar cell will become very small. Also, you get a lot of current leakage because of small band gap. So basically, anything, if you can get something between 400 and 850 or 900, you are doing pretty well. Silicon does very well because it goes from 400 to 1000 roughly, or it's even, you can go to shorter wavelengths. But then, the problem with that is your open circuit voltage typically doesn't exceed 0.6 volts. All right. If you make the band gap very narrow, your open circuit voltage for the solar cell cannot exceed the band gap. It's just impossible. So typically, if you want a solar cell to give something like, operate at 0.8 volts or 0.7 volts, you need something which is actually of the order of something like little more than one electron volt band gap. Okay.
Thank you, sir.
Good morning, sir. Sir, my question.
Yeah, we can interact. We can.
Oh.
Now I request Dr. Milan Bera to introduce Dr. Amitabh Jha.
This one, okay, Professor. Yes. Yes, yes, yes. Hello, hello, okay. Yeah, good afternoon, everybody. Please be seated. I think this is the last lecture before lunch. So after this lecture, we'll have a lunch together. Yeah. First of all, thank you, Professor Jayant Kumar, for a wonderful talk regarding this polymer chemistry. And as a organic chemistry, I found it is a very informative for all faculties and students. and it covers both chemistry and also physics. And now I want to welcome our second speaker from organic chemistry, the Professor Amitav Jha. So before starting that lecture, I can tell you some of the achievement, whatever Professor Jha is holding. So Dr. Jha is a professor in Department of Chemistry, Acadia University, Wolfville, Nova Scotia. Dr. Jha holds an MSc in organic chemistry and followed by PhD in natural product synthesis and medicinal chemistry. Professor Jha has a combined experience of over 25 years in both industry and academia. And his expertise are in the areas of organic synthesis, compound characterization, drug design, molecular modeling, and structure activity relationship. He has published more than 80 research articles in peer-reviewed journal and also 2 important patents. His current research interests include development of drugs to treat various types of cancer and to explore the application of psychedelics to treat certain mental disorders. And Professor Jha Group is responsible for design, chemical synthesis, purification, and complete characterization of drug candidates. So just I am looking to topic of the Professor Jha today's presentation. He will be delivering on the topic of green methodologies involving multi-component reaction. As an organic chemist, I know actually in the lecture of Professor Jayant Kumar, he told that when you are doing any work or any reaction in lab, that is okay for publication purpose, you can do it. But if you want to commercialize those things, it is very difficult for us. So we know that as an organic chemist in our lab, we can synthesize so many things, we can develop so many methodologies. But if we want to commercialize those things, then we need a robust process or green or sustainable process. So I think the Professor Jha's lecture will be helpful and will be benefited for all the students and young faculties. And so I am inviting Professor Jha to deliver your insightful lecture.
Thank you, Dr. Bera. At the outset, I would like to thank the organizers, Dr. Mona Lisa Mukherjee, Dr. Selvamurthy, and other people who are involved with this. I'm an alumni of Delhi University and I did my PhD with Professor Parmar. And it is because of Professor Parmar that I have gotten this opportunity to actually meet with you today. My research is in the area of medicinal chemistry, and you cannot do medicinal chemistry without doing organic synthesis. So today, what I'm going to discuss with you, I will not talk about the medicinal aspect of my research, but I will be talking about the synthetic aspect. In fact, something, a type of a theme that I was able to gather over the 20 years of or 25 years of my research. And so I've selected some of the green methodologies that we have developed, and I will be sharing those with you. So chemistry in my lab, in the medicinal chemistry, we are focusing in drug development. And specifically among these, we are working on selective estrogen receptor modulators, topoisomerase inhibitors, analogs of curcumin. Curcumin is basically a chemical found in haldi, a spice that we commonly use, and histone deacetylase inhibitors. So some of the molecules that have shown good activity in this area, I'm kind of sharing their structures with you. Now, in organic synthesis, one of my interests is cascade reactions. A cascade reaction is a reaction where you put a number of components together and they react in a cascade process. And basically, you do not have to do multiple step synthesis. You just get all the multiple stuff done in one part. So for this, we'll be talking about like multi-component reactions. One of the reactive intermediates that my research uses quite a bit is quinone methides. So I will be talking about quinone methide chemistry. Povarov chemistry, Povarov reaction is also a multi-component reaction, and we have used the Povarov reaction to make some special type of molecules. And N-acetyluminium ion chemistry, again, it's a type of reactive intermediate that enables you to make different types of interesting molecules. So some of the molecules we have made using these types of chemistry are again shown here. And as you can see, it allows us to make different type of cyclic and heterocyclic molecules with interesting structures. The last one you can recognize has a steroidal framework. The anthrazolene structure before that, it has possible application in like organic semiconductors and so on. So green chemistry, what is green chemistry? I don't think I need to talk a lot about this. Green chemistry, probably all of you know, it's basically trying to do chemistry in a sustainable way where you produce less toxic substances, less pollution, develop efficient ways of synthesizing molecules. So there are 12 principles of green chemistry that is often talked about. And in my lab, I may not touch all these 12 principles of green chemistry, but there are some that we actually focus on. So basically, prevention of waste, atom economy, safer solvents and auxiliaries, design of reaction efficiency, use of renewable feed products, reduce derivatives and catalysis. So we focus on these. There are other aspects that I haven't worked on them so far, but it's likely that later, my work might involve some of those as well. So as I said, within the green chemistry aspect of my research, that's the focus. Again, I'm trying to define here what's a multi-component reaction. As the name suggests, basically several components are added together, and that leads to formation of molecule that you want to make. So if you look at the cartoon that is shown there, basically the top scheme shows how you can actually add one compound to the other. So this top scheme right here is showing you one step at a time. So, you take two components, join them together, then you add the third one and so on to get there. Whereas in a multi-component reaction, you bring several components together and you get to this in just one step. So that's an easy way of showing what a multi-component reaction is. And there are a number of multi-component reactions which are already in use in organic synthesis. So the advantages of multi-component reaction. So this type of chemistry already addresses some of the principles of green chemistry. So as you can see, it addresses atom economy in many cases. It reduces derivatives. You can catalyze such reactions, and the reaction efficiency, because of the way it is designed, it automatically increases the reaction efficiency. Some example of multi-component cascade reactions. So these are all probably can be found in textbooks. Bigenelli reaction, which produces pyrimidine ring there, uses 3 component under various conditions. And if you look into this, there are tons of different conditions reported in literature. And this chemistry has been used many times to make many important compounds. The Bucher-Briggs reaction that uses a ketone, potassium cyanide, and ammonium carbonate, and with conditions it makes an Hadentoin type-like molecule just in one step. Gewalt reaction, again, it's giving you a cyclic thiophene derivative starting from 3 components. dihydropyrimidine reaction. This reaction is similar to Biginelli reaction. And in fact, if there is a lot of similarity between the two, even if you look at the product, they look somewhat similar. So on, like, I mean, I just don't want to go over all of those. So, I mean, you can see that there are a number of multi-components reaction which are already in wide use in organic synthesis. Strecker reaction is one of the reactions that allows us to make alpha amino acids. You can see the structure is an alpha amino acid. Mannich reaction is aminomethylation of active methylene compound, a very widely used multi-component reaction. And this Petasis reaction is actually a reaction which uses boronic acid, and there is a similarity between the Mannich reaction and Petasis reaction, and they produce similar type of products, although the mechanism is entirely different. So this was to highlight that multi-component reaction can actually work and can give you interesting molecules. Another reaction, which is also a multi-component reaction. Now this one, Ugi reaction, it actually gained prominence recently, and it is one of the recent reaction which got the name, it was named after the discovery of this reaction was done by Ugi, and it's a 4-component reaction, and in conditions it makes a dipeptide molecule. So a dipeptide molecule normally, just use 4 components and you get a dipeptide. And this also allows you to make unnatural dipeptides. So that can be used in, like making molecules which are analogs of certain bioactive peptides, and they can possess different types of biological activity. In my presentation today, you will see that I have used in many of my reaction, Mannich reaction as well as Petasis reaction. Another reaction that I told you in the beginning, Povarov reaction. So I've used them, and I've used them to, again, not just using 3 components, I've added more components to that and have produced molecules of, interesting molecules with them. So the first one that I'm going to talk about is, a Mannich reaction. So here is a simple Mannich reaction. In a Mannich reaction, you start from a molecule that has an active methylene or a phenol, which is also, you can write the structure of a phenol as in the keto form. So phenol is a permanent enol form of a keto product. So that's why, a molecule like a naphthol can do a Mannich reaction. In the Mannich reaction, you need an aldehyde and an amine. So if you react the 3, you get a Mannich reaction. Very simple, straightforward reaction. What I plan is that how about I keep everything, and on the aldehyde part of the molecule, I have a hydroxy group, and eventually I'm able to cyclize the 2-hydroxy to give an ether and make a cyclic molecule. That was the intent. So I wanted to make certain hydroxy aldehydes and use hydroxyaldehyde to make this type of molecule. I looked into literature, it was not known, and it looked that it sounds doable. So I started to do this reaction. And when I did this, I made these hydroxy substituted aldehydes. And so the idea was that this hydroxy substituted aldehyde will first give the Mannich product, and then dehydration between the 2-hydroxy will cyclize and will give that product. So that was expected. When the reaction was done, I did obtain a product, but the product was not what I expected. In fact, when I did the reaction, the product obtained was that one over there. And as you can see, if you compare the expected and obtained product, the amine group was supposed to be attached at that part, rather in the obtained product, the amine was actually right next to this carbon bearing oxygen. So that was interesting. I did not expect, because what I was noticing here is that the framework of the molecule had changed. Okay, there was some sort of a rearrangement apparently to get that molecule. And another interesting fact was that a minor product obtained was this. And if you look at this product, it's a manic product. It has phenol, it has the amine, and it has a CH2 group. And that CH2 group, you can make that compound using formaldehyde. So if you do a manic reaction using formaldehyde, you can make that compound. So it was quite puzzling that how am I getting this compound when I'm not using formaldehyde? Okay. And we were able to, I mean, again, if you compare the structure of the product that we obtained and the expected, they're very related, they're very similar. But we were able to confirm that we indeed got the amine attachment there by doing the X-ray crystallography. So again, it was a puzzle. How did this compound form? And then we actually came up with a mechanism, and this mechanism was supported by the byproduct that was isolated. The byproduct, which we could not explain because we did not use formaldehyde in the reaction. That compound gave us the clue how that compound was formed. So this is the molecule I'm talking about. In fact, there was another molecule like 4-5% yield was this particular bisphenol molecule. And these were very helpful in coming to the mechanism of the product, how this was forming. So basically, you can, once you have these three compounds, you can see that the reaction can happen between an aldehyde, amine, and hydroxy group to form an aminal. Okay, like where you have the aldehyde group attached to a nitrogen and oxygen. Okay, and then a cyclization is happening between these two. Okay. However, how can you explain a cyclization of these two right here? Because you see it's a primary hydroxy group, and primary hydroxy group would rather rearrange and then form a primary carbocation. And we were not seeing our product. Actually, if we were to explain our product using this particular molecule, then it has to have a primary carbocation, or else this would not work. So this wasn't explaining it entirely. However, it was helpful that these two compounds were seen, and we can think about the formation of these two compounds by doing a manic reaction with formaldehyde, or just reacting two equivalents of phenol with formaldehyde. And these two compounds have actually already been known in literature, having made by this procedure. So what we are proposing is that our compound is not forming this intermediate, rather the hydroxyaldehyde is undergoing a retro-aldol synthesis, retro-aldol condensation. So it's a reverse of aldol condensation, where formaldehyde is breaking off from the molecule to form formaldehyde and dialkyl, the alpha-alpha dialkyl aldehyde. So here is the mechanism that we are proposing. The retro-aldol reaction happens and it produces the two components. Then the formaldehyde molecule and amine as well as phenol react to form the manic base, and then this manic base under high temperature actually does another degradation step, and it forms the reactive intermediate quinone methide. So if this was an oxygen rather than a CH2, this molecule would have been a quinone, but because it's a CH2, we call it quinone methide. And since it is not aromatic and wants to become aromatic, it's a good reactive intermediate. So basically, the quinone methide is being formed. And as you can see, in the retro-aldol reaction, this aldehyde was released. That aldehyde reacts with the amine released in this step here and forms an anamine. So there is an anamine formation, and this anamine does a hetero-Diels-Alder reaction between the quinone methide and the anamine and does a cyclization to give this product. Okay, so this sounded, based on the isolation of byproduct, this sounded that this actually is working. Then what we thought, okay, how about we try to make this compound not using this compound, rather using the individual components. Why make this if it is breaking down already? So use the aldehyde and formaldehyde separately and see if the reaction works. And when we tried that reaction, it actually did work. Okay. Also, if we take this mannich base and react it with this aldehyde, that also gives the product. So basically, as you can see, there are cascade of reaction happening here. The reaction undergoing in this cascade is there is retroaldol reaction happening. And after the retroaldol, mannich reaction is happening, enamine reaction is happening, and then deamination reaction to give the quinone methide, and finally heterodiels-Alder reaction. So there are 5 steps happening in one reaction part, okay, and leading to this product. And there's an alternative way that you can actually do each one of this step one at a time and still get the same product. So of course, this is a much better process to actually, rather than doing 6 or 5 steps, just do it in one step. So as I told you, when I did this 4-component reaction, I was indeed able to get the desired compound. And in fact, in some cases, the yield was close to approximately 94%. So when you talk about the overall yield in a particular reaction, especially in the synthesis of natural products, if it involves, let's say, 10 steps or 20 steps, you can start with kilogram of the first step, and you might end up with few milligrams of the final product. Okay? Here, 5 reactions are being done in one part, and the yield is 90%. So that tells you that, each step, or if you break the yield down between each of these steps, it is basically very high for each one of them. The next reaction that was a derivative of this project, I found out that this molecule splitomycin is a histone deacetylase inhibitor, and it is actually sold by Aldrich and Sigma as a standard. Whoever is working on histone deacetylase inhibitor, they can buy this chemical from them and use it as a standard. When I looked at my When I looked at this product from here, I thought that I can actually convert this molecule into splitomycin analogs. So that's how the 2 projects are related. So I got this product in my previous project, and if I can do some modification to this particular compound, I can produce splitomycin. So basically, what I intended to do is to break this amyl bond, specifically this carbon-nitrogen bond here, that will give me what do you call that? A hemiacetal, and the hemiacetal can be oxidized to make a lactone. So that was the idea. So hydrolyze this aminal into hemiacetal, and then oxidize this hemiacetal to to the lactone, and that will give splitomycin analog. So splitomycin, there are several different ways of making splitomycin. This would have been one of the new procedure to make splitomycin if it worked, and when we tried it, it actually indeed worked. So we used aqueous PTSA condition to hydrolyze the aminal into hemiacetal, and then oxidation using Jones reagent, and we have tried actually several other reagents, and it goes to the product splitomycin analogs in quantitative yield. When I was doing this, it came to my mind, okay, we are able to get to this step in one step. So we use 4-component reaction and make that compound in one step. Can we actually extend this whole thing and get this product in one step, or maybe get the final splitomycin analog in one step, rather than using this as a starting material to do these steps, can we do all of this in one part? And we attempted doing that. And when we attempted doing that, what we found is that we were actually able to get to this hydrolyzed product, this product here, in one step. We were able to get that, and the yield was in the range of 39 to 71% for 14 examples. And all we needed to do is we introduced ethanol water mixture in the reaction, and that gave us this product. Now, can we do the oxidation also in the same part? Technically and mechanistically, this was not possible, because if you add an oxidizing agent right in the beginning, it is going to, there are a number of things here which are oxidizable, so it is going to interfere with them. So what I eventually did that we performed this reaction, and rather than isolating this product, we evaporated all the solvent and added the oxidizing agent into that, and it indeed worked. So without isolating this, we were able to get to the splitomycin analog in one step. The oxidation, as I said, we did with Jones reagent first. Jones reagent uses chromium trioxide, not quite a green reagent. Okay, it's actually very toxic. So we were wondering, can we use some other reagent which is rather green in nature? And when we tried using the bleach that you use in your house, it worked, but the results were not that great. It was very slow reaction. And one of the chemical that is expensive, but it works beautifully, is IBX. Okay, so we used IBX, and with IBX we were able to also convert the aminal into the lactone form in the quantitative yields. Now IBX is a it's a hypervalent iodine-based reagent, which is commonly used for oxidation. So the whole step is shown here, and overall there are, as you can see, there are 6 steps happening. And if you look at the least, the smallest yield we got, 36%. The overall yield was in the range of 36 to 69%. 36% overall yield over 6 steps means that every step is giving an average yield of 84%. Okay, and a 69% of overall yield means that the average yield for each step is about 94%. Okay, so you can clearly see that cascade reaction can actually improve the efficiency considerably. Even for the splitomycin analogs, we were able to get X-ray structure, and they were unambiguously characterized. Then we extended the quinone methide chemistry to different types of reactions, and we found a way of making dihydrocoumarin analogs using quinone methide chemistry. Okay, so there are lots of molecules which can be characterized as dihydrocoumarins. They are interesting, but they have interesting biological properties. Some of them are actually found in nature. So the process we developed was we reacted salicylaldehyde with amine, 2 equivalents of amine and an aldehyde, and we obtained this product here. Now this product is actually again a multi-component reaction where 2 equivalent, you can call it, if you look at all the components in the product, this can be seen as a 4-component reaction because 2 equivalents of amine is being used. Okay, so we did this reaction and we got this compound, but before that we did this reaction in stepwise fashion as well. Okay, so what happens is that salicylaldehyde reacts with the amine to form this the aminal at the aldehyde position, and then under heat conditions it decomposes to give a quinone methide, and that quinone methide actually reacts with with the anamine, and anamine is formed by reaction of the aldehyde and the amine. So that's how the anamine is formed, and they two react together and gives a, it gives the heterodyl-Solder reaction and gives the product here. So that's how we were able to make this compound. And further to this, we were also able to hydrolyze this into semi-aminal and also convert that into cyclic lactone. And these dihydrocumarins were containing an amino group attached at position 4 of the dihydrocumarin. Okay, so in another approach, we thought that, okay, in this chemistry, we are using heterodyl-Solder reaction. So what is a heterodyl-Solder reaction? Probably every chemist knows what's a Diels-Solder reaction. Okay, so heterodyl-Solder reaction is when one of the atoms in the ring is a heteroatom. In most cases, whenever you replace carbon with a heteroatom, the electronics changes. What happens is in a regular Diels-Solder reaction, the diene part is electron rich and the dienophile part is electron poor because it contains often esters and hydride type groups on it. Okay. In a heterodyl-Solder reaction, it's the opposite. The diene part is electron deficient and the dienophile part is electron rich. So in the two examples I showed you before, you would have noticed that the diene was quinone methide, which is of course electron poor, and the dienophile was anamine, which is electron rich alkene. Okay. We wanted to actually find out how much of the electron donating or electron withdrawing effect should be there in the dienophile. So we thought of using this particular molecule as a dienophile, and in this molecule you can see there are two esters which are electron withdrawing, and then it also has a vinyl ether which is electron donating. So it is kind of a push-pull alkene. Okay, and we were thinking in the beginning that this reaction is most likely going to fail, but that did not happen. In fact, it did give us a product, and we got again a mixture of products. Some of these products are, pretty. You can look at them and say, okay, they make sense, because if you have aldehyde, amine, and phenol, the simple Mannich reaction will form. If you react amine with this particular, the push-pull alkene, this product will form. These are all known reactions. We obtained these two products as well. And these two products, if you break them down, they look like they're product of the hetero-Diels-Solder reaction. So if a hetero-Diels-Solder reaction happened between the expected the quinone methide and the push-pull alkene, you would get this product, the second one. However, the major product was this. And in the major product, we had an amine attached here, whereas in the expected product, we have an ether there. Okay. So again, explanation was not too difficult. Since this molecule was forming in the reaction, if this molecule reacted with the quinone methide, that would produce this product, and that is a major product. Okay. So we were able to, without much of a difficulty, explain what the mechanism of this reaction would be. So it forms a Mannich base, then amine reacts with the push-pull alkene to form an amine type push-pull alkene, and when that cyclizes with the expected quinone methide, it gives us the major product. If the alkene is the same that we used, then we would get this second number product. And we tried various ways to reduce these two compounds, but we were unable to completely eliminate them. We were still forming a little bit of those compounds in the reaction. So in this, there are 4 steps happening in one part. We have formation of Mannich reaction, deamination, anamine formation, and finally the hetero-Diels-Solder reaction. Now, switching gears to a different type of reaction that involves formation of, which involves use of Povarov reaction. So Povarov reaction is another multi-component reaction. In this reaction, what happens is a very simple reaction. You form a shift base between an aniline and an aldehyde, and that does a cyclization with an alkyne, and it gives you this particular intermediate quinoline, which aromatizes to give you the quinoline product. Okay, so when I saw this reaction, again, it's a very well-studied reaction. Not much is left to explore there, but what I decided is, how about I start a reaction with dianiline and try to do the same reaction on both sides and get this product. Okay. So anthrazolines are fluorescent compounds and have applications in organic semiconductors. So earlier, these types of anthrazolines were prepared by Friedlander synthesis, and this procedure that I was suggesting was not used to make anthrazolines before. So I thought it'd be interesting if it is successful. So when I tried doing this reaction, I was able to form a one-step Provorov reaction. But there was an interesting observation that at the other amine of the phenylenediamine diamine, I had a benzyl group attached. And this benzyl group was actually coming from the benzaldehyde I used. So Povarov reaction is happening, but how come this aldehyde is reacting with the other amine and is getting reduced? Okay. So again, after looking into the reaction carefully, we found that, look, from this step in Povarov reaction to this step, there is an oxidation happening. Okay. So oxidation happening means this molecule is losing 2 hydrogen atoms and H2 to actually form a quinoline. So this one is not completely aromatic. After losing a hydrogen molecule, it produces a completely aromatic quinoline system. So it is producing, a hydrogen gas in the reaction. And from this step, we actually found that hydrogen was actually being used to reduce the imine bond at the other position. Okay, so the products that we made, you can see that under UV light they were quite fluorescent. In fact, the one containing nitro group was not fluorescent, but others with electron donating group were actually quite fluorescent. So basically, as I mentioned to you, the usual Povarov reaction is happening, but then there is the intramolecular hydrogen transfer that this part is getting oxidized, and the released hydrogen is being used here to actually reduce that imine bond in just one step. So we thought, okay, whatever we wanted to make at the outset, we were not able to make. We made some interesting observation during our research. Can we still make the molecule we wanted to make? Okay, so if you look at this molecule, you will notice that this is benzylated, and it is actually relatively easy to remove a benzyl group. Okay, so the opportunity I saw is that we can remove the benzyl group, produce an amino group, and now try another Povarov reaction on this amino group to get the product. And when we did that, we indeed obtained the product. And this was the first report of the synthesis of anthrazoline, which was unsymmetrical. The Friedlander synthesis only produces symmetric anthrazolines, and this procedure, we were able to make anthrazolines with unsymmetrical aromatic group. In fact, we can change all these 4 aromatic group on the anthrazoline ring. And by that, if you paid attention to Dr. Kumar's lecture, changing the substituent can actually change the optical properties quite drastically. So, it could be of importance that way. Okay, now I've talked about Povarov reaction. I've talked about quinone methide chemistry. The other reactive intermediate that I'm interested in is use of NSi aluminium ion. So I'm going to share some of our recent work on the NS aluminium ion, we found a paper reported in 2002 that this alkyne containing carboxylic acid and this amino benzyl alcohol in presence of gold catalyst was actually forming this ring. So again, multiple bonds are being formed in one reaction. We thought, can we do this reaction where we don't use expensive gold catalyst and we are able to make this in a relatively simple way. So this particular, the pentanoic acid is actually quite expensive itself. 1 gram cost about $150 US. So I thought that maybe I can get the same result if I were to use levulinic acid. This molecule is called levulinic acid, and it's a biofeed. What I mean by biofeed is it is actually produced from cellulose, and it is a renewable chemical. You can make it in any quantity possible. So basically, degradation of glucose into furan ring, and then the breakage of that furan ring produces linoleic acid. Very cheap chemical. You can get liters for about $10–20. So the chemistry we developed for achieving the same type of synthesis was, we started with levulinic acid and reacted it with methyl chloroformate to make a mixed anhydride, and that mixed anhydride was then reacted with this the same benzyl amino benzyl alcohol, and this cyclization actually gave us in the formation of the same ring. Now, if you look at this, we did not have to heat the reaction. The reaction happened at either sub-zero or at room temperature, and all the chemicals that we used were very cheap, and we were able to get the same result as the one used in gold catalyst. After we developed this reaction, okay, again, let us go into the mechanism of this. Pretty straightforward. When you react chloroformate with a carboxylic acid, it produces a mixed anhydride, which is pretty well known. And amine reacts with mixed anhydride and forms an amide. The amide, because it contains a keto group in the neighborhood, it cyclizes to produce this hydroxy compound, which after dehydration produces an NSi aluminium ion. So if you pay attention to this molecule, look at the nitrogen. That's an iminium nitrogen with a double bond, and on the nitrogen there is an acyl group. So that therefore it is called an NSi aluminium ion. NSi aluminium ion is traditionally known to be highly electrophilic. So nucleophile in the neighborhood attacks that and does the cyclization. So in this step, although we are using two components, but we are forming several bonds in this step. So two nitrogen carbon bond is being formed, as well as a carbon oxygen bond is formed. This one pot cascade reaction. So we wanted to then expand this to make steroidal framework containing nitrogen and oxygen. So basically making heterosteroid, a man-made steroid, which are not natural, but they do contain the shape of a steroid molecule. So that molecule right there, you can see it has an aromatic ring. It is estradiol, 17-beta estradiol. It's a female sex hormone. It has a plethora of biological activities. And the first ring right there is aromatic. Okay. And what we wanted to make was a molecule like this, where again, it has a steroidal nucleus, and the ring, in fact, two rings side by side are both aromatic. So this is what we wanted to make. This actually shows you an overlap of estradiol as well as the molecule that we were planning to make. And you can see that they actually overlap pretty well. So there is a phenyl ring, and this phenyl ring, which is not overlapping, is because there is no counterpart in estradiol. But other than that, the molecule is overlapping pretty well. So the approach we wanted to follow was start the reaction with amino naphthalene and attach an acyl group at position 1, reduce the ketone into an alcohol. Now we have a benzyl alcohol and amino group that we talked about in the previous slide. And now the keto acid can actually do the similar type of cyclization I showed you in the previous slide and form steroidal type nucleus. And when we tried this, we were actually successful. Now, but in this process, there were a number of, hurdles. To acylate the number 1 position of the aniline, you cannot do this directly using an acyl chloride on aniline because aniline itself is highly activating group. So because of being highly activating, it actually forms a quaternary ammonium salt with the acyl chloride and the reaction doesn't work. So the textbook procedure is acylate the amine and then do another C acylation. Okay. We tried that, we were not successful even doing that. So we used a reaction where the acylating reagent we used was actually an alkyl cyanide, and we used 2 Lewis acids, the BCl3 as well as AlCl3, and after working up, we actually formed this reaction. I am forgetting the name of this reaction. It is actually a modification of Friedel-Crafts reaction, which uses 2 different types of Lewis acids to achieve this. So when we tried that, we were not sure if this is going to work, but it was working beautifully, and we were able to make this molecule. The next step had, borohydride reduction was pretty straightforward, and we had already developed the procedure to actually cyclize the using the keto acid like levulinic acid to make molecules like this. So we were indeed able to make 12 examples using this. And again, the similar kind of a mechanism that I showed you before, that it is going to first form the amine is going to react with the carboxylic acid and finally form an amide, and then the amine cyclizes with the ketone to give you the hydroxy pyrrolidine ring. Dehydration of that produces NS-aluminium ion, and the nucleophile attacks there to give the product. So we successfully achieved the synthesis of heterosteroids. Okay. An interesting thing in this molecule is, if you look at the structure of estradiol has a methyl group here, which is called an angular methyl. And in the product that we were forming using levulinic acid, we were also getting an angular methyl group installed there. So that was where we were actually mimicking what is available in the nature. Another chemistry of making azasteroids, different from what I showed you before. We envisioned that starting from amine and this particular alkynoic acid, again, I told you earlier that this alkynoic acid is expensive, but we bought it and tried this chemistry because I got this idea that it should work. So basically, we did an amide bond formation between this using EDC, which, amino acid people all the time use this chemistry. So we formed this amide bond, and then use of gold catalyst in the presence of another alkyne, we were able to, in one step, form this azasteroid. Now, this only contains 1 nitrogen in the whole azasteroidal framework. So, first step, formation of amide, and then in the next step, we also, so we did this, and we actually published it in 2015 in Steroids. But then, as I told you, that we have found that this alkynoic acid can be replaced with levulinic acid. We then developed another procedure using levulinic acid to get the same compound, and that worked as well. This we are about to send for publication. So in this chemistry here, again, you form the NS aluminum ion, and then it does a heterodyne solder reaction to give the desired heterostable oil. Now, this is an interesting chemistry that we developed using the Petasis reaction. Okay, and this has a relationship to Amity University. The student that did this work was actually a graduate from Amity University. She worked in my lab for after doing her pharmacy degree from Amity, and she finished her master's degree last year. Her name is Ambreen Siddiqui. Okay, so she did this work in my lab. Petasis reaction, as I showed you in the beginning, is basically if you use an aldehyde, a boronic acid, and an amine, it joins them together. It's a multi-component reaction. Another example of Petasis reaction is this time, this particular aldehyde, boronic acid, and in place of amine, this indole molecule is used, and it also does the Petasis reaction. In fact, the amine can be displaced with indole. This is a nucleophile. Indole, the free position of indole is quite nucleophilic, so the reaction happens. Our plan was use the chemistry like this and replace the amine part with actually phenol. Okay, so amine is nucleophilic. Phenol can also be nucleophilic. If you look into the electrophilic aromatic substitution of phenols, phenol acts as a nucleophile. So we should be able to make xanthine type molecules using this chemistry. When we tried doing this reaction, we actually got a couple of very interesting results. Okay, so we were expecting to make this molecule, which is a xanthine, but when we did this reaction, we actually formed a product which was unexpected. Okay, and this is also xanthine, except that it doesn't have the substitution, phenyl substitution here. So if you compare the starting material and the product, you will notice that this red constituent, the boronic acid, did not attach here. So it looked like that if I don't use boronic acid, probably and do this same condition using these two, I should be able to get that one. I tried that reaction, did not work. It only works when we have boronic acid in there, and so the job of boronic acid is probably it is doing catalysis. Okay, so it needs to be there, and we are getting this product. We have figured out a mechanism how that is working, and then in a modified attempt, you see here the condition is neat condition, microwave, and this temperature. So only difference was that we added another Lewis acid. Boronic acid is a Lewis acid. We use copper triplet as well as the Lewis acid, and now the expected compound that we wanted to make, we were able to make that. The downside here is one of the things that we don't like as much is that the yields are not great, but we were able to make this compound. Now there are different ways of making xanthine molecules, but this one is actually using boronic acid is the first synthesis of xanthine using boronic acid as a modified Petasis reaction. And the mechanism is here again, looks like very busy slide. Like it works in the boronic, in the Petasis reaction, a hydroxy group actually attaches to the boron first, and then the boron gets attached to the aldehyde. Now at this point, this bond breaks, and then at this CH2 group between the two aromatics, this converts into, in presence of the copper triplet, this forms a carbocation, and this phenyl group then actually does a rearrangement, and then in the last step, this 2-hydroxy group after this boronate ester hydrolysis, those 2-hydroxy group actually dehydrate to make that molecule. So there are a number of steps happening in this mechanism. Maybe that is why the yields are lower, but indeed a new procedure to make xanthine type molecules. So in conclusion, multi-component reactions offer a convergent synthesis of complex scaffolds through a network of reaction equilibria, finally yielding the product through an irreversible step. So a number of steps in the multi-component reaction are actually reversible, but the final step is irreversible, and that's why you get a certain product and it doesn't reverse back to something else. So what happens here is that even similar functional groups have different fate. You would have noticed in some of the mechanism, formaldehyde is giving one type of reaction, whereas the aldehyde containing the enolizable hydrogen is giving a different type of reaction. The overall yield of the multi-component reaction is generally better than if each steps are done individually, separately. And we have employed this multi-component reaction to make different types of heteropolycyclic molecules that includes, anthrazolene, that includes azasteroids, that includes, certain dihydro coumarin type molecules. And in the aspect that is similar in these reactions is that they use reactive intermediates like phenol methyl, aluminum ion, and carbocations. So we were able to demonstrate using these reactions that multi-component cascade processes are indeed very environmentally friendly and very useful. And I would like to, these are some of the students who have actually done synthesis. Here is Ambreen Siddiqui, that was alumni of Amity University, and some funding agencies that funded this. Thank you.
It was a really nice presentation with all the variations of multi-component reaction and all. So I want to know, you have mostly used microwave, right, for
Yes,
your transformation. Does it work for the thermal heating and all?
Does it work for?
In thermal conditions, while you heat,
What kind of conditions you said?
thermal condition.
Yes, many of these reactions that we are doing also work in conventional conditions. Microwave reactions, we found that they actually give better yields. So that's why we have used them. But yes, they can be done under thermal conditions as well.
Okay. And when you are going for different derivatives, like changing the groups, so did you find any difficulty in isolating products with some derivatives and all? Because when we make libraries, it often happens, sometimes the reaction doesn't go with some substrates.
What we have found is that, basically whenever the reaction doesn't work, there is a reason why it doesn't work. So let us say we can predict based on mechanism that electron withdrawing group should work better. We actually see that they indeed work better. And so in some cases, yes, we were unable to make certain analogs with certain functional group on the molecule because mechanistically it appeared improbable, and that was confirmed when we did the reaction.
Yeah, sometimes decomposition also occurs
Yes.
within the reaction. Okay,
True.
okay, thank you.
Any other?
Hello. Sir, in the first two multi-component reaction, you used morpholine for the secondary amine. Can we use other cyclic secondary amines like aziridines?
Good question. Actually, you probably noticed that in most of my examples, wherever an amine was needed, I was using morpholine. Since we have been doing this reaction for a long time, what we have found is morpholine actually was working best compared to pyrrolidine, pyridine, hexamethylenamine. So there are different commercially available amines, and morpholine in most cases was actually working the best. And you would also notice that in many of our reaction, the amine is not retained in the final product. Okay, so it did not matter to us which amine we used. And because morpholine was giving better, it was working better in our cases, that's why we stuck to that. But yes, we have shown that other amines also work.
Thank you.
Uh,
Sir, that at the starting of the presentation, he told that is cascaded reactions. So basically, whatever the reactions you have showed, Michael, manic reactions, so those things forms intermediates through intermediates. So what is the difference between cascade reactions and normal reactions? Because all forms intermediates, then all will be cascaded reactions. And one more thing, sir, one more question, that you have shown that manic reactions. So basically, you have shown cyclic manic reactions. So is there any chance of forming dual manic or double manic reactions?
Is there a chance
Or double manic reaction?
for manic reaction? Yes. Okay,
Thank
so first part first, you know, what was that, the first part?
Cascaded reactions.
Cascade reactions, yes. So for the cascade reaction, there are some, for example, if you look at a very simple SN2 reaction that you study. SN2 reaction involves, professors tell us, or SN2 reaction involves just this concerted process, one step. Whereas an SN1 reaction has 3 steps, you know, formation of carbocation and so on. So a non-concerted reaction, which is, if it involves 3 elementary steps, it will still be considered one reaction. But in the example that I showed you, it was possible to make some of those intermediates, isolate them, and then do the further step. In fact, we did, in some cases, we made the intermediate, and then we did the next step after on that intermediate to get the final compound, which we were getting in just one part. Okay, so as whenever you are using multi-component reaction, and if they are successful, you can, in fact, individually do some of the steps and then isolate the product and then do the next step. So in some reactions, I counted as many as 6 steps. So you can say that, okay, quinone methide, formation of quinone methide will not survive. Okay, you cannot isolate quinone methide, that's true. But things like enamine, you can isolate enamine. Things like, manic base, you can isolate them. So a lot of those intermediates, you can do single step, and then the next step after that to get the same final product. Okay, now the second part of your question was, again, what was it? Double manic reaction. Yes, they work. I have done some reaction on double manic reaction. So if you have the right substituents on them, you can do double manic reaction. So let us say, you have 2 hydroxy group on a benzene ring. So if you use 2 equivalents of aldehyde and 2 equivalents of amine, you can get double manic reaction on that compound. And there are a number of examples where that has been done. Yes.
Yeah. Hello, sir. A very comprehensive talk indeed. Just one curiosity I have, that in your first approach, where you showed your hydroxy carbonyl compounds were undergoing a retro aldol kind of thing. So did you try with salicylaldehyde? Or did you speculate any retro aldol condensation there?
We have done a reaction with salicylaldehyde. A retroaldol doesn't happen, and we actually get like a benzoxanthene type product. So,
which was again unexpected one.
No, it was basically expected, and it worked nicely. So if you see that retroaldol is not possible in
Salicylaldehyde, yeah.
So it worked as expected. And in that reaction, actually, we did not use any amine. It was just an active methylene compound and the salicylaldehyde, and that led to the formation of benzoxanthene. In fact,
so you used nephthol there, right? Nephthol, aldehyde, and the amine part. So then what were the products? What?
Okay, if I am using a manic reaction in which I'm using salicylaldehyde, that reaction doesn't work.
Okay.
It doesn't work. It's basically a mess of many spots on the TLC.
Yeah.
Okay. But we did a reaction in which we use beta tetralone,
okay,
and salicylaldehyde. Okay. And just 2 component reaction, and that led to formation of benzoxanthene. Again, it was a different procedure than all other reported procedure of benzoxanthene formation. And in fact, that is one of my highest cited paper, synthetic paper, not a review. There are reviews that get more citations, but so since it cannot do a retroaldol, it stays like that,
Okay.
and it undergoes the reaction. But when I do the Mannich reaction using salicylaldehyde in a normal way, it does not work.
Okay, yeah. Thank you. Just a small one more.
Yeah.
So, okay, yeah, thank you so much. Okay.
I'm not asking a question, a compliment and a comment. Compliment to Professor Jha, I fondly call him Amitabh, is that I think Professor Mukherjee, you should invite him for at least 1 week for short course. I think it will be very beneficial to the students because the symposium today is molecular chemistry and smart materials. In the generation, as Professor Kumar said, and one experience for last 20 years on polymeric materials and polymeric nanomaterials, which I learned in your center from 2001 to 2005, you need small molecules. And drugs, almost all drugs are small molecules. And all applications, all materials that you make are from small molecules. So the small molecule synthesis and click chemistry is a very handy reaction today. Are to be made very smartly and greener way. I think what Dr. Jha did that very beautifully with his examples from his own lab. And he can give a course, basic organic chemistry course involving his own research. Very useful. And I'm sure, I don't see many students here. Maybe students are online attending this symposium and they would be, there must be many who must have been online at their own places and benefited by that. Yeah. And so that is a compliment. And the comment is that he made the whole reaction sequences which he used, which were done in his lab. He explained them so beautifully. And also, I want to make one, in the very beginning of his talk, he said that the mechanism of the reaction was elucidated by studying the byproduct of the reaction. I don't know how many students are here who are doing total synthesis or the multi-step synthesis and come up to the mechanism. And students often purify, get the required compound from the column chromatography and forget about the side products which are obtained. And even in the pharmaceutical industry, I'm sure Dr. Jha, Sunil have worked in pharmaceutical companies for some time. I didn't though. I mean, they say the side products are most important than the main product which is performed, right? So therefore, I think this is a lesson again for the students to learn that never dispose of the other fractions from the column chromatography. Who knows, they may give you a more useful product. So that is one, I think, example for the students to be taken into account for all their research in synthetic chemistry. Their byproducts or side products, whatever you want to call, they're very important to study at ISO. Thank you. Thank you.
Professor Jha, very interesting talk and very informative one. I had a very quick question. Means I have not done this component cascade reaction ever. So very frank to you. So I just want to know how difficult is when we are adding all together,
then getting a product. The final product will be like, along with the main product, there will be lot of final byproducts also, as sir told, and you have also spoken. So how difficult it is to isolate that? If we perform one by one single step compared to that, how difficult it is to purify the main compound from the, in this multi-component cascade reaction? And another is, what about the yield? Is it like one component, if we go one single step, the yield will be more, or the yield is more in the multi component cascade reaction? Okay. Yeah. Okay, okay. Thank you. Thank you. Thank you.
Sunil Kumar Sarma. So very good afternoon. I hope you have all have done your lunch. So it is my pleasure to introduce today's esteemed speaker, Professor Sunil Kumar Sarma sir, who is a senior professor in the Department of Chemistry at the University of Delhi. Professor Sarma's academic journey is one of dedication and excellence. He obtained his PhD in organic chemistry from the University of Delhi in 1992. After completing his master in chemistry in 1986 and BSc in chemistry in 1984, both also from the University of Delhi. So his research interests are diverse and encompass various fields, including organic synthesis, biocatalysis, polymer science, nanotechnology, and chemistry of natural products. So Professor Sarma's extensive research experience spans across several renowned institutes worldwide. He has served as a research scientist at the University of Massachusetts, Lowell, and Boston College in the United States, as well as research fellow at Copenhagen University in Denmark, and CSIC, which is a Spanish National Research Council in Spain. So throughout his career, Sir has contributed and recognized with various honors and awards. He has published an impressive number of research papers, review articles, and hold a patent. His contributions have garnered significant attention with near about 4,500 citation with 36 H index and 110 I-10 index. Moreover, Sharma sir is a dedicated mentor, having supervised 23 awarded doctoral theses. His commitment to the advancement of science and education is truly commendable, and we are honored to have him here today to share his expertise and insights. So please join me in welcoming Professor Sunil Kumar Sharma sir.
Very good afternoon to all of you, and thank you, Dr. Mishra, for the kind introduction. Also, I would like to convey my thanks to Dr. Salwamurthy and Professor Mukherjee for giving an opportunity to visit here. It is my first visit to Amity University, and I'm very much impressed with the kind of infrastructure and the young faculty over here. And I wish you good luck. So you see that after lunch, when we have to take another lecture, so people say that we have to give a dose to the audience, otherwise they will not listen. So that's why we have to talk about some drugs so that you can become alert. You see that when we take a drug, I do not know, particularly for the students, this is the query from the students. Have you ever considered that when we take a drug, whether the whole amount of the drug is used for the purpose for which it is taken, or only a small amount is taken? For example, when the doctor prescribes that you have to take the paracetamol, the doctor says that you have to take 3 tablets of paracetamol, 600 mg in the morning, in the afternoon, in the evening. So I do not know whether you have really considered seriously whether the 600 milligram of the tablet of paracetamol is used for the purpose for which it is taken. And I tell you, the situation is very, very bad. In some cases, only 20% of the drug reaches the target site. And in some cases, only 1% or even less than 1% of the drug reaches the target site. For example, cisplatin is an anti-cancer drug, and it is used to treat the cancer. And only 1% of the drug reaches the target site, and remaining amount goes to the untargeted sites, which is responsible for the cytotoxicity. And I would like to cover today these challenges, how we can overcome these challenges, that is the low drug efficacy, and how we can enhance the drug efficacy. And today, before lunch, Professor Parmar has mentioned that most of the drugs are small molecules. For example, the aspirin is acetyl salicylic acid, is a small molecule, naproxen, and 80% of the drugs are small molecules having a limited molecular weight of less than 500. And many of these compounds are very less soluble in water. So solubility in water is another issue. So that's why today we will talk of synthesizing some amphiphilic molecules which can be used as drug delivery agents and which can encapsulate the drug, which not only enhance the solubility of the drug, but also can help in bringing the drug to the target site. So I would like to start with this diagram, and particularly for the students, and if you are from the pharmacy, then you should know that you can see that when the drug is taken, then the drug comes out of the body and only a small amount is used for the purpose. Sometimes it is converted into metabolites, and sometimes the concentration of the drug falls very rapidly. And for therapeutic use, the drug has to be maintained in a particular window that is called therapeutic window. And if the concentration of the drug is lower than the therapeutic window, then it is ineffective. So just to maintain the concentration of the drug in the therapeutic window, the doctor prescribed the tablet to be taken every 6 hours, every 8 hours or so that we can maintain the drug in the therapeutic window. You see that
a number of starting materials have been used to synthesize drug delivery agents, and there is some requirement for the drug delivery agent. The first requirement is that the drug delivery agent or the building material or the starting material for the drug delivery agent should be biocompatible and biodegradable, because if it is not biocompatible, then our body will not accept the compound and we cannot use it for the drug delivery purpose. So keeping that into account, we have been working in utilizing the well-known simple molecules to synthesize the drug delivery agent, and this involves glycerol and the carbohydrate molecules, for example, glucose, glucitol, and also polyethylene glycol. You see that there is a very interesting story about the glycerol, because we use glycerol in our household and it is non-toxic. And if we go back to 1940, then the glycerol was produced from epichlorohydrin, because at that time, people thought that we cannot meet the demand of glycerol, and they were producing the glycerol from epichlorohydrin. But you will be surprised to know that since 1940, all the industries which were producing glycerol from epichlorohydrin have been closed, and rather there's a reversal of industry. Now the epichlorohydrin is being produced from glycerol. And you may be wondering, why is it so? Because the large quantity of glycerol is being produced from oleochemical and biodiesel industries, because now people are considering to synthesize the synthetic diesel or synthetic petrol. And this is being produced from the oleochemical and biodiesel industry. And in this process, 10% of the diesel is glycerol is being produced as a byproduct. And we cannot use the whole of the glycerol which is being produced. And that's why they are converting the glycerol to epichlorohydrin. So the consuming the glycerol, which is produced from the oleochemical industry, is a big challenge for many state governments. And that's why we decided that we should make the value-added products from glycerol. And since it is non-toxic, since it is biocompatible, since it is water-soluble, and it is also soluble in organic solvents, so we decided to use glycerol as one of the building blocks. And we have successfully carried out the oligomerization of glycerol to synthesize diglycerol, triglycerol, and polyglycerol. Also, you see that the glucose is another building block that we have used. Glycitol is another carbohydrate, and we have used polyethylene glycol. Polyethylene glycol is an FDA-approved material which is used in many syrups as a co-solvent, and it is also non-toxic. So we are working to synthesize drug delivery agents using these biocompatible, well-known biocompatible materials, that is glycerol, polyethylene glycol, and carbohydrates. And we are synthesizing a wide variety of amphiphils. So people who are just new to this area, I would like to mention that the drug delivery agent should be amphiphilic, because it should have the both lipophilic group and as well as the hydrophilic group, because most of the drugs which are available in the market are hydrophobic and they have limited aqueous solubility. However, our biological fluid is aqueous based, and so the drug delivery agent should itself be soluble in aqueous medium. So if we have the hydrophilic group, it will make it soluble, and if it is having the lipophilic group, that will help in encapsulating the drug. So that is the idea, that our drug delivery agent should be amphiphilic. Now these drug delivery agents should be soluble in aqueous medium and should form the micellar aggregates or aggregates, so that they have a hydrophobic cavity inside. So the hydrophobic groups comes together. So there is a hydrophobic cavity, and the hydrophilic groups remains on the outer periphery. And this cavity, which is hydrophobic, helps in encapsulating the hydrophobic drugs inside. And thus, this not only enhances the solubility of the hydrophobic drug, but also helps in circulating the drug, hydrophobic drug, in our body for a longer duration. So you see that amphiphils are not only used for the biomedical field, that is for drug delivery, but amphiphils are used in many other industries, for example, for personal care products, for bioremediation, for catalysis, for enhanced oil recovery, and many other things. And also surfactants, because all the surfactants are basically the micellar aggregates, as you know. Also, I would like to mention here that surfactants are known for hundreds of years. It is not a known, I mean, it is a very well-known chemistry, but still the surfactants based on soaps and detergents cannot be used as a drug delivery agent because they have a very high concentration at which they form aggregate. And we are interested in molecules which can form aggregate at very low concentration. So particularly the drug delivery agents are more helpful or more useful for tumor targeting. And I would like to explain this with this slide. You see that if we compare the tumor cells and the normal cells, then you can see the difference. The tumor cells are fenestrated and they have wide gaps. And a small molecule, if it is given as a drug for tumor targeting, then it cannot distinguish between the normal cells and the tumor cells because of its small size. But when we have the drug is encapsulated in a bulky material, in a drug delivery agent, then because of the bulkier size, this cannot pass through the tumor cells, normal cells, and can easily go through the tumor cells. This is one advantage. Another advantage is that the tumor cells are slightly acidic. The pH is 6 to 7. And as compared to the normal cells, normal cells have pH in the range of 7.1, right? So if we can design and develop the drug delivery agent, which is sensitive to the pH, then this strategy can be helpful in releasing the drug to the tumor site. So that's why we thought that we should make the drug delivery agent, which is pH sensitive, right? And in this endeavor, the ester group, because it is a well-known chemistry, the ester groups are sensitive to pH, and our drug delivery agents are mostly based on ester functionality. So you see that glycerol has very simple structure. It has two primary hydroxyl groups and one secondary hydroxyl groups, and it is biocompatible. It exhibits good chemical stability and inert under biological conditions. And as we have already mentioned that the diglycerol, triglycerol, and polyglycerol that we have synthesized again have only two kinds of hydroxyl groups, primary and secondary. But to proceed further, we have to distinguish between the primary and secondary hydroxyl groups. And chemically, it is not easy because whatever reaction we carry out, then it will be difficult to distinguish between the primary and secondary hydroxyl groups, and we cannot carry out the reaction selectively at the primary position or at secondary position in presence of primary. So that is the reason that we wanted to develop a method which is efficient and can easily distinguish between the primary and secondary hydroxyl groups so that they can be used further for the synthesis of drug delivery agents. So for that purpose, we turn towards the enzymes, because enzymes are known for a long time that they have a good chemoselectivity, they have a good regioselectivity, they have good enantioselectivity. And considering our experience of using the biocatalyst for variety of purposes, we decided to use a hydrolytic lipase. This is called Candida antarctica lipase, and we use immobilized enzyme Candida antarctica lipase, which is known as Novozyme 435. You see that if we carry out acetylation using vinyl acetate of either glycerol, diglycerol, or triglycerol, then the reaction selectively occurs at the primary position and the secondary groups remains intact. This is a simple chemistry that we can make use of the enzyme to distinguish between the primary and secondary hydroxyl groups and carry out the protection of the primary hydroxyl groups in the presence of secondary. So we simply use this strategy to synthesize the drug delivery agents. And once we carried out the protection of the primary hydroxyl groups using the enzyme, then the secondary hydroxyl groups can be functionalized chemically. And we have done so by attaching the different functionalities at the secondary hydroxyl groups. For example, we have carried out the attachment of azide group or we have carried out the Mitsunobu reaction and attached the phenyl moiety, or we have carried out the esterification reaction through this secondary hydroxyl group to have this kind of functionality. And once we have these kind of building blocks ready, then we again can carry out the deacylation again simply by using the enzyme, the same enzyme, Novozyme 435. So please note that we can use the enzyme for carrying out acylation, and we can use the same enzyme to carrying out deacylation, and in a selective manner. So here we observe chemoselectivity because, sorry, regioselectivity, because only the primary positions were acylated. And in this case, when we carried out deacylation, we observed chemo as well as regioselectivity. So you see that using this strategy, we have carried out azidation, we have carried out Misirov reaction, we have carried out esterification, and then simply we have carried out hydrolysis, and all these building blocks have been used successfully for polymer synthesis. Right? Now, when we talk of a drug delivery agent, then one another important factor is the balance between the hydrophilic and lipophilic groups, because the aggregation formation occurs only if they have a good balance between the hydrophilic and lipophilic moieties. And for that purpose, I tell you that when the HLB value is between 10 to 12, that is considered to be a win-win situation, because when the HLB value is less than 10, then the material may be insoluble in water, and if it is the more than 12, then it may not form the good size of aggregates. So that's why when we decided to use these building blocks to synthesize polymeric materials or amphiphilic polymeric materials, we took into account that there should be a good balance between the hydrophilic and lipophilic factors, so that the HLB value remains in the desired window. You see that we have used two strategies. We have synthesized the linear polymers using enzymes, and these polymers, linear polymers, have functionalities which can be used to fine-tune the physicochemical properties of the polymers. As you can see over here, that this is a linear polymer, and this has some functionalities, and these functionalities can be used to attach the different kind of hydrophilic groups, hydrophobic groups, or the cell targeting agents. And then these kind of amphiphiles then aggregate in aqueous medium, form nano-size aggregates or micellar aggregates. So you see that when we started from glycerol treated with vinyl acetate, carried out the simple vinylation at primary position, acetylation, and then methylation and azidation. And this azidoglycerol was the one building block. And then we synthesized the PEG diester from PEG diol simply by carrying out oxidation using the KMnO4, and then we carried out the esterification reaction. And these two building blocks, this is the azidoglycerol and this is PEG diester, can be mixed together to subject to esterification reaction, and finally we get the linear polymers of this type. And these linear polymers can then be decorated with different kind of hydrophobic groups using the esterification reaction or simply the click chemistry. Because I tell you that this institution name is Click Chemistry Institution, and this is very viable, and I'm happy that we are also following click chemistry to synthesize the drug delivery agents, and you may be interesting to know all these kind of reactions. So these amphiphilic materials are then studied whether they can form nano-size aggregates by using the DLS, by using cryo-TM, and by using the fluorescence techniques. And also we wanted to know that whether these aggregates can encapsulate the drug or dye material, right? You see that we have also incorporated our linear polymers, the polyglycerol dendrons. So you see that this is generation 1, this is generation 2, and this is hyperbranch polyglycerol. Also, we have attached the normal alkyl chain, long alkyl chains, and perfluoroalkyl chains. The perfluoroalkyl chains have a unique characteristics in terms of their hydrophobicity, in terms of their linearity, and we have obtained very interesting and wonderful results in terms of drug delivery capacity that I would like to discuss. So these are some of the features of perfluoroalkyl chain. For example, they exhibit strong hydrophobicity, well organized assemblies, all trans helical configurations because it is all trans, and some promising antifouling properties, and they play potential role in drug delivery and biomedical. And as compared to their normal alkylated counterparts, they have very low critical aggregation concentration. So this critical aggregation concentration is the concentration, it is a minimum concentration at which these amphiphiles form aggregates. And the CAC should be as low as possible, because then the amphiphiles will remain in the aggregated form at very low concentration, and they can circulate in the blood for a longer duration. Because if the CAC concentration is high, then they will degrade very easily. And this is the key difference between the normal soaps and detergents and this kind of amphiphiles, that they have very low CAC value as compared to the normal surfactants. So you see that this is to give you an overview that what kind of amphiphiles we have synthesized. So we have attached the dialkyl chains, we have attached a different kind of hydrophilic moieties, like we have attached PEG, we have attached G1 and G2 dendrons, and we have attached alkyl as well as perfluoroalkyl, or both the fluoroalkyl. And we have observed a very unique pattern when we move from the dialkyl to monoalkyl, monoperfluoroalkyl, and diperfluoroalkyl in terms of their aggregation behavior. Because sometimes they form micellars, sometimes they have the tubular shape, and sometimes they have this double micellar shape. So what we observed was that when we have the perfluoroalkyl chain, the CAC value is approximately 10 to power 2 times lower than the alkyl chain. I mean, they have very low aggregation concentration at which they can form micellars. And the perfluoroalkyl chains are also non-toxic, right? So this is another finding that we have reported. We have also compared the different size alkyl chains. For example, C11, C13, C15, C18, and C20. And what we observed was that the longer the alkyl chain used for this purpose, then the less is the toxicity. So as compared to C12 alkyl chain, the C18 alkyl chain is less cytotoxic. And this kind of aggregates can have better adaptability or better acceptance in the biomedical field. So not only the polymeric materials, we have synthesized amphiphiles, small molecules. And the advantage of small amphiphiles is that their molecular weight is fixed, because in polymers, we never get the molecular weight of the same size, because there are molecules, there are some short chains, some long chains, and we use average molecular weight. But then the small size amphiphiles, the molecular weight is fixed, and we can have a better control in their structural properties, because it is a small molecules and we can handle them in a better way. So we have synthesized a wide variety of amphiphiles, for example, twinned amphiphiles, Gemini amphiphiles, dendronite amphiphiles, and Janus amphiphiles and dendrimers. And also we have synthesized the different kind of AB, A2B, AB2, A2B2, where A and B refers to hydrophilic and hydrophobic. So we can have one hydrophilic group, two hydrophobic groups, and then one hydrophobic, two hydrophilic, two hydrophilic, two hydrophobic, and so on. And we wanted to see that which is the best system, whether we should go for AB system, A2B system, AB2 system, or A2B2 system. You see that we have used very simple, easily available, the cheap material. For example, para-hydroxybenzoic acid we have used. So the para-hydroxybenzoic acid, starting from para-hydroxybenzoic acid, we simply carried out the Birch-Robin reaction with the this glycerol derivative, and we get this AB2. You can see that this is a AB2 building block, because here we have a carboxylic group on one side and this acetylenic moiety on the other side. So we can use two different kind of chemistries. We can use the click chemistry to attach two different groups attached, and we can use the esterification reaction to attach here the different moiety. For example, here we have used the hydrophilic azide, and hydrophilic azide can be attached through this AB2, and it will give us this kind of building block, which is then subjected to esterification reaction, and then finally we have this AB2 amphiphile, right? We also have synthesized this AB amphiphile, and we wanted to compare the which system is good, AB amphiphile or AB2 kind of amphiphile. Not only that, we have this is the simple chemistry. I mean, this is the chemistry I have explained. So those who are interested in chemistry can just quickly go through it. That starting from glycerol, we synthesize the diacetyl glycerol, and then diacetyl glycerol was subjected to Mitsurobu reaction, and then we get this intermediate. This intermediate was subjected to hydrolysis. We get this diol, and then diol was simply treated with propyl bromide to give this diacetylenic compound, and this diacetylenic compounds was then subjected to the synthesis of amphiphile by using click chemistry and esterification reaction. So you see that not only polyglycerol, we have attached this carbohydrate azide. You can see that here we have used the diglycerol, and we have used the polyglycerol, and we have used the PAG unit. So we have varied the hydrophilic group starting from PAG, polyglycerol and polyethylene glycol and carbohydrates. And similarly, we have varied the hydrophobic chain starting from long alkyl, short alkyl, perfluoroalkyl, and we wanted to have a different combination so that which system works better. So this is another A2B2. A2B2 was synthesized from isothalate moiety. So this you can see here that this is the A2B2 spacer that we have used, or A2B2 core, and we can use a click chemistry to attach the hydrophilic moieties, and we can use a simple esterification reaction to attach the long alkyl chain, right? And this core was synthesized by a very simple step of reactions, as you can see that starting from isothalate, we carried out the Mitsurobu reaction and then subjecting it to hydrolysis, and then carried out the reaction with the propyl bromide to have this moiety, and then simply this was followed with the click reaction was followed, and esterification was followed to synthesize the various kind of amphiphilic architectures. So these are the different compounds that we have synthesized. We have varied the PAG size also. For example, we have attached PAG 550, PAG 1000, PAG 1500, PAG 2000, just to see that which system works better. Here we have used diglycerol. Instead of glycerol, we have used diglycerol, and using the same chemistry, we carried out this azidation, and then this was subjected to polymerization reaction. We get this linear polymer, and then by using the click chemistry, we have attached the different kind of moieties. As you can see over here, we have attached the PAG unit through this azide moiety, and we have this kind of amphiphiles ready. Triglycerol has also been used. For example, you can see here that we have this is the triglycerol moiety, and we have synthesized amphiphiles based on triglycerol. For triglycerol also, we first synthesized triglycerol starting from epichlorohydrin and this glycerol acetonide, and then once we get the triglycerol, it was again subjected to the same acylation reaction followed by Mitsurobu reaction, and we get this intermediate, and which was hydrolyzed and followed the same chemistry, that is click chemistry, as well as the esterification reaction. So these are the different kind of compounds that we have synthesized based on triglycerol. We have used the carbohydrates as a building blocks also. We use a glucitol, D-glucitol. As you can see that the D-glucitol has 6 hydroxyl groups, and we synthesized the glucitol monoacetylene, starting from glucitol. And now in this glucitol monoacetylene, there are two kind of functionalities, two primary hydroxyl groups and two secondary hydroxyl groups. And we have successfully attached the different kind of functionalities through the primary and secondary to get finally the amphiphiles of this type. So you can see that we have used the click chemistry reaction to attach the hydrophilic moiety at the secondary position and hydrophobic moiety at the primary position. Also, we have attached the hydrophobic moiety simply through esterification reaction, and we have attached the hydrophilic moiety through click reaction. And here also we have attached, in this case, we have finally carried out reproduction of the acetonide, and we have this kind of amphiphils ready. So this is the strategy that we used for glucitol. Glucitol was first treated with acetone, triacetonide, and then this triacetonide was selectively hydrolyzed by using 70% acetic acid, and we get this glucitol monoacetonide. And this glucitol monoacetonide was then tosylated, because tosylation is a bulky group, and it will occur at the primary position followed by agitation, and we get this diazo compound. And then the diazo compound was used further for the synthesis of amphiphils. As you can see that we have attached different kind of functionalities. So these are the different amphiphils that we have synthesized by using glucitol as the starting material. In another approach, we have used diazo moiety, the diazo group, for synthesizing the stimuli responsive drug delivery agents. And you see that we have synthesized polymeric materials having diazo group. And the diazo group initially, because of its higher stability, initially it has a trans geometry. And by irradiating the UV light, we can convert the trans to cis. And if we have a trans geometry and we can encapsulate the compound and then irradiate it with UV light, then what will happen? That on irradiation of UV light, this will change to cis. And this, because initially we have a compact packing because of the trans geometry, and when we irradiate it with the UV light, then it will be converted to cis, and the total packing is not very compact, and it will help in releasing the drug. And we have used the Nile red. Nile red dye is a very commonly used as a model compound to confirm encapsulation, whether the drug delivery agent can encapsulate the drug or dye or not. Because the Nile red has a photochromic behavior. When the Nile red is present in a hydrophobic environment, then it exhibits fluorescence. But the moment the Nile red comes out of the hydrophobic environment, then the fluorescence is quenched. So initially, the Nile red is encapsulated and it is present in the hydrophobic environment, and we have a strong fluorescence. But the moment we convert the trans geometry to cis, then the Nile red comes out of the system, because now the inner of the cavity is not equally hydrophobic. And that's why the Nile red comes out, and we have a decrease in the fluorescence. We have carried out then again cis to trans, again irradiated UV light and converted to trans, and we found that some of the Nile red comes back, but not a whole of the Nile red comes back into the amphiphilic system. So we can say that these kind of systems, which is showing the stimuli responsiveness towards UV light, can also be used for drug delivery. You see that we have confirmed the size of the nano aggregates using the cryotime studies, as you can see here, and we have compared their size by DLS also. And in one of the studies, we have used nimodipine and curcumin also. So nimodipine and curcumin, nimodipine is an anti-inflammatory compound, and curcumin, you know, that is the ingredient. This is an ingredient of this haldi, and it is useful for many purposes. And in a recent study, it has been reported that curcumin can be a good candidate for Alzheimer's disease, which is the brain related. But the problem is that for the brain related diseases, a drug has to cross the blood-brain barrier to reach the brain, then only it is effective. And the problem is that many of the drugs cannot cross the blood-brain barrier and they cannot reach. And that's why people are working to develop a method which can bring the drug to the brain. And we thought that curcumin has the same issue, because curcumin cannot cross the blood-brain barrier. And we thought that if we can encapsulate curcumin in a drug delivery agent, then which can itself cross the blood-brain barrier, then it will be able to help to bring curcumin to the brain and can be used to cure Alzheimer's disease. So in this direction, we have used the encapsulation of curcumin. And we found that we can encapsulate good amount of curcumin, and we can also develop a release mechanism dependent on the pH, dependent on the UV light, and which can be helpful in releasing the drug at the target site. So you can see here that this particular system having the perfluoroalkyl chain and G2 dendron is very effective for encapsulation of the curcumin, as you can see here. And since our polymeric system is ester based and ester is sensitive to pH, and at pH 5, we have seen that this polymeric system disintegrate and it will help in releasing the drug. So what we have also found that this perfluoro system is more robust, means this can circulate in the blood for a longer duration as compared to the normal alkyl chain, and it has lower critical aggregation concentration also. In addition to that, I mean, this is a release mechanism. We have used pH dependent system, we have used UV, we have used enzymes also to release the drug, because you see that our drug delivery agent is ester based, and there are many hydrolysis enzymes in our body which have hydrolytic properties. And if our drug delivery agent comes in contact with this hydrolysis, then they can help in hydrolyzing the ester functionality, and they can help in releasing the drug from the drug delivery agent. And we have established that on the basis of using the enzyme, the same enzyme, that is Novozyme 435. So you can see there that without the enzyme, there is no change in the fluorescence intensity, but in the presence of the enzyme, the fluorescence intensity keeps decreasing. So that shows the release mechanism. And we have compared the perfluoro system with a normal alkyl system also. Now, because for drug delivery agent to be successful, it should bring the drug, it should go inside the cells, and it should bring the drugs inside the cells. And we have done the confocal imaging studies to establish that this drug delivery agent can bring the cargo inside the cells. And also we can see that in the 24 hours time, the intensity of this in the imaging, the intensity increases with time, and that fully established that this drug delivery agent can bring the cargo inside the cells. So with this, I would like to just wind up, and because I'm basically a messenger, and this work is being carried out by a young force of PhD students like you have, and I really appreciate. And also, I'm very thankful that we got generous funding from the different funding agencies, for example, DBT, DST, DRDO, DAD Germany, BIRAC, CSIR, Delhi University. And a good part of this work has been carried out in the laboratories at Freie University Berlin, Germany. And also, initially, this work was carried out in the laboratories at UMass Lowell, in the laboratories of late Professor A.C. Watterson, Professor Jayant Kumar, and Professor Parang also helped in carrying out the toxicity studies of some of our compounds. And with this, I would like to end. I have a long association with Professor V.S. Parmar, who was my PhD mentor and then colleague, and also a collaborator for a long time. And with this, I would like to thank you all. So if you have any questions, then I would be happy to answer them.
Yeah. Hello, sir. It was a very informative talk. Sir, I have a quick question regarding the photoresponsive drug delivery system. Where you showed the trans and the cis conformation
Yeah.
again the drug release.
Yeah,
Sir, you have shown that the drug release is by the UV light.
yeah.
Yeah, so but we know that the UV light for the body, it is not applicable that
Okay.
much.
Yeah,
So
good
how
question.
friendly you will find this drug
Okay.
delivery system?
Okay. Actually, there are many stimulants, not only the UV light is one of them. UV, pH, ultrasonic waves, and for example, for tumor targeting. Because for tumor targeting, we can attach some tumor targeting compounds and which can bring the drug delivery agent along with the drug to the tumor cells. And once the drug reaches the tumor cells, then in that particular portion of the tumor, if we irradiate with UV light, I think it is, I mean, not that harmful. So that is the purpose for tumor targeting, because for different diseases, for different purposes, the different stimulants have to be used. So for tumor targeting, the UV light can be safely used, localized UV irradiation. It is not that we have to expose the whole body for the UV light. The localized this thing can be used.
Sir, even the penetration power of this UV light is less compared to the near IR light.
Yeah.
In that regard,
Actually,
even
I tell you that it is not that we have to continuously, because if we consider the UV exposure, then even we have the UV exposure outside also. I mean, that depends on how much UV exposure. So that's why people have to use the protection light. I mean, the protection cream also, UV cream. So our purpose is to just establish that in acute cases, if we have a tumor and we can localize, if we can just direct the drug delivery agent along with the drug to the tumor site and can irradiate in a localized manner, then perhaps it is better. Because you see that these options, कि जैसे आपको कोविड का जो वैक्सीन आया, normally a vaccine development takes 10 years, but considering the acute situation all over the world, they said that, oh, 1 year time is good enough. Because if a person is in terminal position, I mean, like, then even for cisplatin is highly toxic, and for chemotherapy only cisplatin is given, and you see that it is very troublesome, but there is no other way. So we have to weigh the options, that whichever is good, because first thing is that to save the life, and then the secondary effects. So same is for the UV light, that if a person is in that condition and UV light can be one of the measure, then perhaps we should go for that.
Sir, if we can replace that cis or trans, which is UV mediated change in the isomerism, if we can change something more with the near IR light photoresponsive, that system, do you think
One
it
thing
will-
more I tell you, that the UV light that has mentioned, it is 350.
Yes.
So we are coming to, I mean, this almost near to the visible range. I mean, it is not that much, right? So what is your second question? Sorry.
I was telling that if this delivery system could have been modified with the photoresponsive group, which is in the visible light or a near IR light, then that would be a.
When we do the basic research in the academic institutions, this is to establish a concept, right?
True.
Because it is not that we are launching.
Yes.
Because when you go for that stage, then you have to consider many things. So first thing is to establish the concept that UV can be used as a stimulant for drug delivery, and then further secondary things are there, that we should attach some group so that to bring it to the absorption should come to the visible range. So that is another possibility. Yes.
Thank you. Thank you so much.
Yes.
Yeah.
Very informative talk.
Thank you.
Indeed. Since I also have started working in the area of material biology. So my one question, you have done the work with the cancer, lung cancer cells, right? Lung cancer, am I right? So what about the healthy lung cells?
What is it?
Healthy lung cells means the normal cells. How your materials are behaving towards the normal cells?
Sorry, I'm not getting you. What is that?
No, you have shown the cytotoxicity. I think they are killing the cancer cells, right?
Yeah.
So what about the normal cells?
Oh, okay.
the materials.
So, I mean, you were talking about how to distinguish normal cells and human level, how to.
Yeah, no, I'm telling, they are killing the cancer cells.
Yeah, yeah.
Very good. What about the normal cells? Are they
You-
cytotoxic?
Again, the thing is that cancer is such a situation.
Yeah.
Where so far, not even a single method has been developed, which is 100% safe and which is going to cure only the tumor or cancer. So we have to pay for that because I gave the example of chemotherapy. Chemotherapy, because this cisplatin analogs have been developed, carboplatin, nidaplatin, and there are many other things, but they have limited approval. And even today, there are two kinds of chemotherapies because sometimes the preliminary chemotherapy, they give carboplatin, that is not troublesome. But ultimately, they have to go for the cisplatin. And cisplatin, I tell you, the only 1% reaches the target site and the 99% goes for the toxicity. And it has nephrotoxicity, of acute toxicity. But thing is that when it is a do or die situation, then we have to go a long way to go for cancer treatment. There's a long way to go, and there's not such a even a single cure that which is you can say the 100%.
No, I'm not telling. Yes,
Yeah,
of course, that is a major bottleneck for cancer therapy when we are going. So
Yeah.
that's why we are not able to reach the milestones. But the thing is that comparative chart should be there, that at least, yes, even if healthy cells they are killing, but this much percentage, that was my only question.
Yeah, we have to actually go a long way because
Yeah.
in the academic laboratories, I mean,
Yes.
we are doing
The
the
basic-
small experiments, and when we go to this product development side, then
Of
many
course,
more things
that
have to
also
take into
again, the material, even though it is working good in cancer cell line,
Mhm.
and when we are going to the 2D to 3D, then depending on the microenvironment, the material property changes.
Mhm.
Not only, even if it is working with the 3D, very good spheroids, organoids, but again, with the immunity of the people, say immunocompromised, the
Mhm.
material property again changes.
Yeah.
That's why we are nowadays coming up with personalized based medicine, what US is looking for. So, so anyway, that was my only question. That what about the healthy cells? Because sometimes the healthy cells are also disrupted
Mhm.
with this cancer cells. So that was it.
Okay, thank you.
Hello. Sir, in your one slide, you showed that trans is transform into cis.
Sorry, I'm not. Your
Ah.
voice is not clear. Actually, you come closer. You are.
Sir, in your one slide, you showed that trans compound is transformed into cis. Trans compound is
Translucis.
Yes.
The same UV light.
Yes. How it is characterized?
Oh, the diazo chemistry is a very well-known chemistry, and diazo group, it is very much dependent on the UV light, and it can easily be trans to cis and cis to trans, because this is a quantized. There are quantized levels, and it is well known. It is well established that cis can also be converted to trans. You are talking of stability. The trans
Yes.
is very stable and cis is not, and that's why we cannot convert cis to trans. But geometrical isomerism, particularly in the diazo, is not such that we can use the UV light, which should be quantized, which should match with this cis to trans transformation, and it is well known. There is not even a single frequency. On multiple frequencies, trans can be converted to cis, and cis can be converted to trans.
Oh.
It is well established.
Oh, thank.
Okay. Yes, please. Mhm. Yeah. Oh, you mean the molecular mass? There is a GPC, for example. We can characterize the molecular mass is GPC. What is the molecular mass? And they do not have a exclusively the same molecular mass. If we say that we have used the polyglycerol of a molecular mass, average molecular mass 1000. So it may from 800 to 1200. So these are the polymeric materials. So all the polymers, their molecular mass is the average molecular mass, and we use this GPC for characterizing their molecular mass. Yeah. Again, this is a reactor structure. This is all well known, and people, I mean, we have also quantified that how many primary hydroxyl groups are there, how many secondary hydroxyl groups are there, and this can be done chemically also. Because if we do some chemical reaction, for example, if we first subject it to tosylation, right, and then tosylation will occur only on the primary hydroxyl groups, and then we treat it with acetic anhydride. Then the secondary positions will be acylated. Then we can record the NMR, and we can just quantify that how much is the primary and secondary. All this is well defined. Okay. Yeah, it is published. Yes.
Sir, whatever the molecules you have synthesized, so I've seen that maximum all are symmetric molecules, like it has no chiral centers.
There's no
Chiral centers.
There's no chiral center, yeah, except carbohydrates. When we use carbohydrates, the carbohydrates itself, they are inbuilt chiral centers.
No, means my question is that is it like that for drug delivery means system, whatever the in target cell you are for the receptor you are targeting, so chiral molecules will give better result or achiral molecules will give better result?
You see that it is a good question, because when we talk of drug delivery agent, then most of the time we are focusing on the physical phenomena, physical parameters, like that the drugs, when we have to encapsulate a chiral drug. I mean, you may write that if we have a drug delivery agent which is itself chiral, then it may exhibit a different behavior towards a chiral drug for encapsulation. I cannot comment on that right now. But normally our focus is that it is a physical phenomena, completely physical phenomena, because these drugs which are hydrophobic, they are encapsulated because of the various van der Waals interactions, hydrophobic interactions, pi-pi interactions, and aromatic interactions. And for that, the chirality may not play that big role. But you are right that, because we have not synthesized anything, and I cannot comment on that part. Maybe when our drug delivery agent is chiral, then it may exhibit little bit different. It may be able to distinguish between the chiral drugs also. But our focus is not towards that part.
No, because sulfur linked many compounds are there for anti-cancer and those things. So there are many molecules I have seen that it is chiral centers. There are so many stereogenic centers. So that's why I have asked.
That many people have synthesized drug delivery agents based on amino acids, which are chiral. And to the best of my knowledge, no one has put too much of focus on their chirality, that drug delivery agent is synthesized from these amino acids, and since it is chiral, so it has shown some properties. Because most of the people, or almost more, I have to check, because that's why, it is too early to say make any statement. But most of the time, I have not seen that they are talking of chirality in the drug delivery agent so far.
Means solubility, it depends on chirality or not. Means
chirality, no.
Because if it is,
it may be different.
Drug delivery agents. He's talking about the carriers. Am I right?
No, I'm talking about you are talking about the chirality in the drug delivery agent, right? Chirality in the drug delivery agent.
Yes.
So what I'm trying to say is that it is basically when we try to, because we are doing two things. We are encapsulating using these hydrophobic interactions, pi-pi interactions, or van der Waals interactions. That is totally a physical phenomena, right? And chirality has no role. Then we are circulating in the blood. That is again a physical phenomena. Chirality has no role because it is not right. And then it is bringing to the target site. The drug is then brought to the target site. Maybe there, if drug delivery agent is chiral, so it may have a different concept, but ultimately it is again a physical phenomena, that how the drug is released from the drug delivery agent. And it is by dilution, it is by presence of some pH, the pH based, or some other things. So people are focusing on the physical phenomena on.
Okay. And one more question, sir. In your slide number 41,
yeah,
can you go to 41?
Just how to go back to 41?
41.
41. No, no. 41, yeah. Okay, yeah. Here, let us start from here. Let's start from here. Yes. Yeah,
Previous one, 41.
41. Oh, okay.
Yeah,
this one.
yes, this
Yeah,
one.
yeah. Huh.
So here that PL curves are there with enzyme and without enzyme. So means I want to know that,
Okay.
can you give short description?
Okay,
that-
what I'm trying to say here, that we have encapsulated, for example, the drug, either curcumin or Nile red, and without the enzyme, there are ester functionalities, and this is safe enough because without the enzyme, without enzyme, there is a slow leaching of the drug. Slow leaching means the system is not very stable, but during some days or time, there is slow leaching when we have alkylated chain. But when we have perfluoroalkylated chain, then we have not observed any leaching. Maybe I can compare it with this one. You see here, I wanted to compare that the drug delivery agent, there is a problem of leaching, that over the time, some drugs comes out on its own, right? When we compare the perfluoroalkyl chain and with the alkyl chain, then you see that there is no leaching. Without enzyme, there is no leaching. But in alkyl chain, there is some leaching. This is I wanted to say.
Okay, sir. Thank you, sir.
Okay. Okay, anything else? Yeah, please. Okay, then we can discuss maybe at later time, right?
Yes.
Thank you very much.
Good afternoon, everyone. So we are coming to the last lectures for today's international conference. So we have Professor Brajendra Kishing. So before start his lectures, so we introduced Professor Singh. Professor Singh has done master's and PhD from Delhi University, and he is postdoctoral scholar at the University of Leuven, Belgium. It is one of the nice place, I must tell, in Europe. So in 2005 to 2007, and then he joined as assistant professor in Delhi University. He is now promoted to professor. So today's all lectures you can able to see from morning, solar cells, and then multi-component reactions, and then we have drug delivery for organic molecules. Now he will discuss about the synthesis of the small molecules or CH activation using the microwave assisted palladium catalyzed reactions. So I welcome Professor Brajendra Singh for your lectures. Thank you.
Thank you for your kind words. First of all, I would like to thank Professor Nalisha Mukherjee for inviting me for this lecture over here. Of course, this is not the first time for me to visit MIT. We have a good friends over here, so we quite keep on visiting the institute, but we love this institute, that's why we are here. And then my mentor, Professor V.S. Parmar, who was the real man behind this program, I believe, and he asked me to come for the lecture. So thank you, sir, for your kind cooperation. I'm a bit, like little sleepy because I ate too much during the lunch time, and maybe I was quite hungry, or maybe the food was too good. I don't know, but there is an effect which I can feel. So if something goes wrong, please excuse me for that. But of course, chemistry wise, there should not be anything wrong, and there should not be anything quoted wrongly. So before I proceed, the title, already Professor Jaz informed you a little bit more about the microwave assisted chemistry. But of course, there was no one who was talking about the palladium and CH activation or CH functionalization. So today I will talk about just one particular topic, that is the regioselective halogenation of heterocycles. Right. So before going there, I would like to just, because we have students in our audience, so they should know like what is the CH activation, what is the concept. So before CH activation concept into the picture, before that, whenever we had to do any derivatization, any functionalization, so what we were doing, we were first derivatizing it as this CH bond to some functional group one, let's say like functional group 1, and then functional group 1 to the functional group 2. But now we have a method by which we can activate the CH bond and directly introduce functional group whatever we want to use. So this method by which we can functionalize this CH bond, that really is a very mild process. You will also see mild process is there. It saves more time and lesser steps are required, because here you need at least 2-3 steps are required to go for the functionalization, and it is done with the readily available substrate. So with this information, I will move further. So as we know, like I'm using this palladium as a catalyst. So everybody knows like what is the role of catalyst. Catalyst itself doesn't do much into the reaction, but they are just a facilitator. They come into the picture and then they leave the product afterwards. So by which they decrease the activation energy of the system, and by which reaction take place at the lower temperature or lesser time, or more productivity is there. So conventionally, if you don't use the catalyst, then of course the activation energy for the reaction is quite higher. But when we use this catalyst, then the activation energy is quite low, and then we can get the product very easily. So this is basically the role of the catalyst. And then the last, the microwave. So by which we can increase the rate of reaction. Because of that, we can decrease the time. The product yields are usually very high. They are very environment friendly because we don't use too much of solvent. So it is very environment friendly, mild condition, and reduced time, because because it can go much faster. So it will reduce time. So I'm not going to discuss much about this, because in this morning it was discussed. So just I will go to my topic, where we have done this, like halogenation of this phenylquinazolone molecule. And this phenylquinazolone molecule, you can see the different some of them are the natural products, some of them are the synthesized molecule, which can be utilized for a different purpose against antioxidant and inhibitory activation, and all these different activities are known for this quinoxylon. This is a very important heterocycle. You can see particularly at 3 position. So 3 position, this quinoxylon is very important. So we wanted to derivatize this, this position, how we can utilize this position for the benefit of medicinal chemistry. Because I'm by training, I'm a medicinal chemistry. So whenever I work, and even the research group work, we always have something in mind, that how we can utilize our molecule for the activity purpose. So we wanted to utilize this benefit of this nitrogen bond, and this nitrogen and this CH bond. So we had this concept in our mind that we can activate somehow this CH bond, and we can introduce halogen over here. Once we have a halogen, we know, like once you have a halogen, you can do n number of reactions with the halogenated compounds. So with this in our mind, so we wanted to replace this hydrogen by halogens. So with that, for that, we chose, like 2 steps for this. So first we synthesize this quinoxylone molecule, and then we started working on whether we can replace this hydrogen with this halogenating agent. No, because for this purpose, we use this succinamide kind of, so it can be bromine, chlorine, or iodine, anything can be possible with the NXA. So based upon this palladium, because we have already worked with the palladium, we are working for last 5-6 years on palladium chemistry. And personally, I have worked on this since 2005. So I have a good expertise with the palladium, so I know how I can manipulate this palladium. So we had this concept in mind that this nitrogen and this hydrogen can be somehow complex with this palladium, and then we can have some success. So with this aim, we started our synthesis. So we did it, and with all these three, like halogenating agent, bromine, chlorine, iodine, and we could successfully obtain this in microwave just within 30 minutes of time. And you can see lot many variations are there. We have 1, 2, and 3. So these R1, R2, and R3 are all three different positions can be very easily substituted, and we can get a good number of example by which we can derivatize many more molecule. So with this, we synthesize with NBS. We could synthesize this set of examples. So we use this for the purpose. We use this NBS, and we could very easily synthesize, converted this into the bromo derivative. So all these bromo derivatives were very easily synthesized within 15 minutes of time. So all these were synthesized. Then we turn our attention to the other halogenating agent, NIS, and with this we could very easily obtain this iodo derivative of this, and with the same set there because we want to see the productivity with our. And here the important thing was that this system is very reactive, so the reaction could be very easily achieved within the 5 minutes of time. So we could obtain the product in 5 minutes time. So we could obtain all this product in good yield. Then with the NCS, we could obtain these chloro derivatives, but with this, once again, it required 15 minutes of time. So with bromo and chloro, it required 15 minutes, and with iodo, it required just for 5 minutes because of the reactivity of NIS. So very easily we could once again synthesize a good number of examples with this iodo derivative. Regarding all this, where you can see like we have changed different R2 groups. So here we could change ethyl, methyl, and all these things, even benzyl. And here the chloro, we have where the different position of a different functional group. So the tolerance of this protocol was quite good with respect to the substrate, this or even the substrate with the halogenating agent. So there was no problem in obtaining the product. Then we actually wanted, as I said in the beginning, that we wanted to check whether we can synthesize some molecule which is used as a drug. So we synthesize this bromo derivative, of course, iodo and chloro also. So, but with this bromo derivative, we could perform this, synthetic application. We have seen with boronic acid, we could do the arylation. So very easily, you see here, bromo derivative could be converted into the alkyl one, and then this cyanation reaction with the help of copper cyanide. We could introduce here the CN group. Once you have a CN group present over here, you can do n number of reactions. There is no problem in doing further reaction with this cyanide group. And then with hydroxylation, we could achieve this. If you could recall, there was one natural product which was this hydroxy derivative. So we could even obtain this in 79% without any optimization. We just literature reported procedure, and we just wanted to see the application, whether it can be applied to our system or not. So it was well tolerated with the hydroxylation, and then with the amination also. So bromo derivative was very easily converted to the amino group. So all the things which were in our target, which we wanted to synthesize, very easily we could synthesize with this protocol, and even not, it can be further expanded. There is no problem in this with this amine. With this amine, you can go for n number of reaction. Either here with the cyanide group, you can go for n number of reaction. With this hydroxy group, you can go. So it has opened the spectrum of this three quinoxolone molecule, where we can have n number of derivative depending upon the activity which it comes to our hand. So with this synthetic application of our protocol, we wanted to see the mechanism how this reaction. As I said, we could very easily understand the mechanism of this reaction, because we are good with this palladium chemistry. So we just did some control experiment to know what are the use of the catalyst or the oxidant which we have provided in the system. So you can see that without the catalyst, this reaction was not possible. Just in traces, which we can see something on the TLC, but we cannot isolate at all. So without this catalyst, it cannot be done. And without this oxidizing PTSA, we can obtain this product, but it in the really less amount, poor yield. So just 15% of the halogenotate product was achieved. So it was somehow suggesting us that both the things, of course, the catalyst and the oxidizing agent is required. So with this, we could very easily describe the mechanism. Very simple, as in case of all metal catalysis. First thing is the cyclopalladation, because this nitrogen and this palladium, they can go for the cyclopalladation reaction. This complex will form, and then in the first step, let's say the cycloaddition. So cycloaddition of this halide will come into the picture, and then here it will give you the complex of this, and then after this oxidizing agent, which helps actually in the reductive elimination. So reductive elimination of this gave us the our halogenated product. So the mechanism is quite simple. There is no complication in the mechanism. So with this, we wanted to see whether we can extend our protocol to some other substrate or other target group or not. So then we thought of this benzoxazine. So benzoxazinone, so it is also well known. You can see this benzoxazinone is also well known heterocyclic compound for various activity. So with this, we had the same concept in our mind. We were not lacking the concept that yes, of course it is there. If this is there, then of course there would be. Okay. So you want to discuss something, or I can continue? Yeah, oh, it's okay. I am not out of the screen, so there won't be any problem. Okay, so with this benzoxazinone, we had the same concept, because here this group can be very easily, this nitrogen can be once again utilized for this. So based upon this, we could once again, this nitrogen molecule, we wanted to utilize the concept of this cyclopalladation with palladium. So with this, we could do the same. So we first synthesize this, and then with this palladium catalyst, we again with this annexes, we could obtain this product with the fluoro, chloro, and iodo derivative. So very easily we could obtain our product. Once again, if you see here, PTSA was once again utilized for the purpose as an oxidizing agent, because it helps somehow in reductive elimination to obtain the product. So all the say condition, if you see the condition, there is a no change in the condition. We just like utilize and really explore the substrate. So then this we could very easily obtain our product nicely with all these three derivatives, this bromosuccinimide, chlorosuccinimide, and iodosuccinimide. And you can see the different variation is quite possible with this substrate. There is no problem in that. So we could very easily use different substrate for the purpose. So with this substrate scope was evaluated. So this NBS was utilized, and you can see here within a 15-minute we could obtain the product in nicer yield. So there is no problem, and just within 15 minutes, and this microwave irradiation was giving the product. Similarly, with iodo derivative, once again this 5 minutes, and then all the products were achieved in really good yield. So actually, we were looking where we can exploit the this palladium and nitrogen kind of interaction, which usually works for it. So iodo derivative we can very easily obtained by this, and then once again with this chloro in this system, it was requiring like 30 minutes of time. So here it was a little bit slower as compared to the bromo and iodo. So this derivative was chloro derivative was also obtained in 30 minutes time with all the same set of substrate, and all these chloro derivative were obtained in a good yields. There is no problem and complication in that. So with this, like once again, we wanted to explore, like whether it can have a synthetic application or not. So we could once again do like, like in this case, so we were running out of time because we have an invitation from this RSC Advanced to submit a paper. So we could not do, all those experiments which we did with quinoxolone. So with this boronic acid, we could simply converted this into the LLZ, or you can see there's a 5 very easily. All this boronic acid, like aromatic, heteroaromatic, and all this can be very easily utilized, and all the derivatives were obtained in really excellent it without any optimization. And then we checked the this application further on gram scale, because it was asked from the reviewer that whether this method can be utilized for the gram scale or not. Then for in the revision, we did this gram scale synthesis, and gram scale synthesis was also achieved in 80% yield. So it can be a scalable reaction. There is no problem in doing this halogenation with this example. So with this information, we wanted to have some control experiment, because we wanted to depict and propose a mechanism for it. So with this, all the standard condition and control experiment we did. And without NBS, once again, no reaction was possible, because there is no possibility of getting bromo derivative. And without this catalyst, once again, it was in an unidentified product. Traces was there, but we could not obtain it, whether it was the product or not, because it was asked by the reviewer. You said like it is a traces of compound, whether it was a trace of your product or something else. So like we could not identify. So it was something on the TLC, not identified at all. And then with without PTSA, once again, it was 31% of it. So this reaction is possible without the organ, but with poor yield. So based upon this, we could propose the mechanism. Once again, the cyclopalladation, as it was in quinoxolone. So this cyclopalladation was there. Then the oxidative addition of this succinimide, halogenating agent, let's say, was there. And then with the help of this PTSA, this reductive elimination, and the product formation could be very easily synthesized. So with this, I would like to acknowledge the person, this person who has worked on this particular halogenation. and the funding agency, University of Delhi, DST, DRDO, and all CSIR. So thank you very much for your kind attention.
Good afternoon, sir.
Hello.
Hello, sir.
Mona Lisa, good afternoon.
Hello.
Mona Lisa,
Yes, sir. Can you see me?
I have reported, yes, I can see you always. Very good.
Sir, we have with us Professor Jayant Kumar
Right.
from Massachusetts. We
I
have,
heard, Mona Lisa, I heard his full lecture. From Jayant Kumar, I heard his full lecture.
and we have Dr. Sunil Sharma, Professor Sunil Sharma from Delhi
Right.
University,
Right,
Professor BK Singh from
Right.
Delhi University,
great,
Professor Parmar
great.
from Delhi University, CUNY, Medars, Amity, and we have Dr. Amitabh Jha.
Right, correct. I heard also his lecture partly from Amitabh Jha, right. Right, great. So you can go ahead.
Okay, sir. Thank you, sir, for coming for some time. Please shower your blessings so that we can do good work.
How can I avoid your order? How can I avoid? You invited, I have to come.
Thank you so much, sir. Thank you. Okay. Parmar, sir, you want to tell something? Parmar, sir?
Hello, Chauhan sir. Namaskar, sir, namaskar. इसने कहा ना Delhi University, she should say first Amity University's man, our man.
Good to see you and talk to you, and thank you for making it possible for all of us to come here, visit Amity University and give lectures to the students.
Right.
And it has been good interaction by the students also with all the speakers.
Right.
I think they enjoyed the talks and the subjects.
Right.
And they had a lot of interaction, questions, and also some, I mean, I think it was quite useful to them, this symposia. And we will try to do more of this kind of short symposia so that if it is running over to 2 days, 3 days, 4 days,
right,
it is boring. I think 1 day and condensed symposia is very useful for students.
But each lecture was very enriching and leads to new ideas, new avenues, new research ideas. I have not heard many lectures like this where there is a lot of suggestions for further research, because I really enjoyed every lecture. I really enjoyed some I heard fully and some I heard partly.
By the way, if I'm allowed to say so to my colleagues here,
Ashok Chauhan ji himself is a chemist. He did a master's in chemistry long time ago, and it doesn't look like long time ago, of course. And then he did a PhD in Germany in polymer science.
Right.
So he's both, we're doing polymer chemistry and we are chemists. But we have the same fraternity.
Right. So being a chemistry man, I really enjoyed more all topics because I was remembering my student days, my PhD days. So Mona Lisa, you have really invited with the help of Parmarji, wonderful people, very worthy people. I was astonished that there are so many ideas. And now I will write to Saikat Datta and Ranjan Patra and Mishra Prasad, Puja Prasad and Saikat are the main persons for this conclave, and also Milan Bera. So all your people are under the leadership, Mona Lisa, you are exceptionally working hard, exceptionally.
Yes.
And when I see so many people sitting over here, the questions, answers were very pertinent. The people, those who asked questions, I was astonished that the speaker very much appreciated the topic of questions. So I'm very happy to see all. In between, I also see the faces of all sitting over here, but I'm very glad that so many people are attending physically and many people are attending online, a number of good. But we will later on sit together to find out 20, 25 points where we should do further research in it. Please go ahead.
Energy and enthusiasm I see. So I certainly, want to congratulate you on what you've achieved because, this energy and enthusiasm and the talent you have assembled will certainly yield rich dividends.
Very right, very right.
So I again want to thank Dr. Mona Lisa Chatterjee, Professor Parmar, and the institution for inviting me. And it certainly has been a mind-opening experience. So thank you very much.
Well, you have very rightly told, mind-opening lecture. Very right, very right.
And I just heard of it, and this is the first visit, but I see the amount of energy I see, enthusiasm and talent, that certainly, I think this place will go places.
Very right. Sir, we will always keep you roped in now. We need your continuous help and advice for decades to come. Decades to come.
Sir, I'm connecting to Professor Jha.
Right, right.
Just like Dr. Kumar, this is again my first visit to Amity University, although I've heard about it for a long time and I've had students from Amity work in my lab.
Right.
Yes, and I also know that we have a program with my university and Amity University. There is a joint program that has been signed. So that was also, and again, there's such a nice place in this Delhi NCR that I'm actually witnessing today here. So to see the kind of achievements Amity is making.
Great, great.
Great experience.
Prasja, I had a major part of your lecture, then I had to rush to other meeting in between. But I'm exceptionally glad and proud. But what wonderful ideas were very, very high power enriching ideas. Now the life of my Mona Lisa and others have become difficult. Now I will chase them to follow all these ideas in the form of research and cooperation, collaboration. All my students and faculty members, I think not very many seminars or workshops, colloquiums are like that.
I'm telling you truly, because in this campus, more than 1,000 events take place like that. But this was really one of the exceptional. And I saw the faces, those who are attending with full enthusiasm, we are rightly full energy. And that has also given me great joy and great satisfaction. Thank you.
So connecting with Professor Sharma, who also gave a wonderful talk related to.
Hello, good evening, sir. I know that you visited chemistry department, Delhi University, almost 4 or 5 years back. You may recall.
Right.
And I heard you about when your activities over there. And I am so glad to learn that you have expanded further. In the meantime, you have opened new campuses all over India and also abroad.
Right.
And I appreciate the kind of work you are doing, because opening new institutions, education institutions is more important than opening the religious places. So it is a greater service to the nation and also the entire world. So I really appreciate, your thought process and also the way you are doing the services. So thank you again for the invitation to the MIT family. And I appreciate the staff and the faculty and the students. They are
Right.
very active and they are very sincere and serious. So
Right.
yeah, I congratulate everyone and thank you very much, sir.
Thank you, Sharmaji. Very right. I'm so thankful. But we'll sit together, all those who are here from NCR, where it's easy to meet together. And for 2-3 hours, I will have consultation with you, exchange of ideas. Because when one day Mona Lisa came to me, sir, I want to open an institution of click chemistry. Although I'm a man of chemistry, but was not much knowing about click chemistry, but my intuition and my sense to grasp new opportunities is tremendous. So I told Mona Lisa, go ahead. Then John Bosses came, and with the Nobel laureate, they connected me. And Mona Lisa knows very well Nobel laureate, his wife. She's almost her friend. And I am astonished in which way click chemistry had developed. And I tell you to all, I promise and tell you all, we will be in click chemistry #1 in the world, because it was very virgin area, not known to much people, but Mona Lisa started it in a way, and these all scientists in an institution, MIT Institute of Click Chemistry, are so brilliant. And I think, how does he collect all students and so? So Mona Lisa, we have to be #1 in click chemistry by the mission, my mission, best of the West and best of the East. All those who are all over the world, we will connect their brains with the brains of Indians. To all my students sitting over here, during my 28 years of stay in Germany, I noticed that our brain, our thinking, our research is not less than anybody in the world. I will not say better, but anybody in the world. And my student, many of you know, I was, after finishing my PhD and all, I joined the institution as head of the research and development department, only Indian in that big organization of plastic and rubber. And after that, I married, because that was my step in the life. First education, then good service, then marriage, and then independence. Then I started, after I found a girl, then the same week, I started on my own venue. And my dear students, 6,000 Germans were reporting me, mostly Germans and mostly also European. I'm not telling to boost it. I don't need to boost. My people know my failure or my success or my plans. But I want to say, if these Europeans and Germans were saluting an Indian, forget about John, saluting an Indian, then we have something very special. And all these worthy guest speakers, those who have come, I'm grateful. They have come here because they know that the process further will be really very wonderful, very beneficial, very fruitful. And that is why they have taken all the trouble to come here. And I thank Paramarji to navigate all this, make it possible. And Paramarji will be now more of my man than in other universities. He's also consultant to many renowned universities in the country. But he told Dr. Chauhan, after knowing Mona Lisa and your chemistry department, I'm very much impressed, and he will spend a lot of time with us here in America. And we will invite you also at my global research hub in New York Island, New York Iceland. I have bought a 175-acre land there, and I'm developing at a global research hub so that the whole world can assemble there, because for many people, it is perhaps easier to reach to the New York than to Delhi. So we will be holding also such seminars. Now, Mona Lisa is going for a long period to Canada and USA and meeting many top universities. And she will also go to the Global Research Hub to see how we can develop also a center of an institution in our Global Research Hub. Dr. Mona Lisa, we should plan in a year or 2 or 3 a conference there at our New York Island campus. It's a wonderful, heavenly campus, and all those have come from USA. I invite them to come with their family there and stay at my campus as my guest. But the only problem is then you will not go back. Then your wife or children will say, sir, we should stay here for long time. So that is the problem. But you can also work from there. But I'm so glad that that such a wonderful exchange of wisdom and ideas. Mona Lisa, I cannot sufficiently appreciate you. You are a unparalleled, unassuming, exceptional scientist and a great human being. As a great human being, and all these faculty member with her will confirm me that you must have not met a person with such combination of research, politeness, and the humbleness. Thank you so much. Thank you, Mona Lisa.
Thank you, sir. Thank you. The last one, sir, Professor Singh, BK Singh, who is
Right.
also a student and now student of Professor Parmar, and now he is a professor of Delhi University. He has given the last talk. Few words from him.
Great.
Good evening, sir.
Right.
I still remember the day when you came to our campus in 2019, Delhi University, chemistry department. And
Right.
invited us for the campus walk. And that time we visited this MIT University, this particular Noida campus.
Right.
And I am a regular visitor of this campus. And I must feel proud because I have a good collaboration in chemistry department, biochemistry department. We work together with a good collaboration. And I must congratulate and thank you for appointing good faculty over here. And we feel privileged and proud to have a collaboration with MIT faculty member over there. So thanks and keep on appointing such a good.
Great. Interesting. I
Thank
heard
you,
also
sir.
partly your lecture. Great. I'm very happy. Your former head of the chemistry, Ramesh Chandra, is like my real brother. Very close to me.
Yes.
And always we met before that tenure, and now he has become a vice chancellor of Bharatpur University, Rajasthan. So I was very closely connected with your department. Once they invited me as chief guest, there was a function outside in an open area, and I met all students, faculty members, and then I went to his room and I saw how closely connected were the faculty members. Great.
Sir, so AICCRS members and the adjunct members, Dr. Mukesh Chaurasia, Dr. Devolina, Dr. Shruti, please come. We all want to thank you that you have given us the time and you have come here and graced this occasion with your blessings. Sir, all of us here. By one.
Thank you, sir, for your blessings. And we will try to do more and more with your. Yeah, myself is Dr. Vivek Misra, sir.
Okay, great.
Sir, Dr. Saika Datta, thank you for your blessings, and we always look forward to your blessings and guidance. Thank you
Right.
so much, sir, for your time.
Great.
Sir, I am Ranjan Patra. So still I remember the ACRB Share Fellowship I got, and in the 15th August, almost 1 year before, you
Right.
me and with full fellowship, you gave the opportunity to visit South Korea. And
Right.
I come back just in February. And
Right.
that paper which I have done in South Korea, yesterday it is got accepted, and this is my 50th publications. So I thank you for your blessings. We will do whatever we can able to do from here.
Great cycle.
Sir,
Great.
this is Dr. Pooja Prasad. Sir, thank you for giving us an opportunity to organize this international symposium and bring such a faculty, such a professor, so that we can listen to him. So it was a very informative and very interesting talk. We learn a lot. So thank you for showering your blessings and giving us this opportunity. Thank you, sir.
Pooja, Saket, Saikat, and you both were instrumental on the front line. Everybody was helping and the guidance, but you were the front line fighter for this conclave today. Am I right, Lisa?
Thank you, sir.
Am
Yes,
I
sir,
right?
rightly said. They are the conveners for this. But
Correct.
yes, Dr. Vivek, Dr. Ranjan, Dr. Milan, Dr. Shruti, Dr. Chaurasia, all of us, Dr. Debolina, all of us helped for this. And but yes, they were the conveners. And I
Right.
must tell you, sir, Dr. Milan Bera has
Right.
brought Dr. Maiti yesterday, and he was so happy. He is the Bhatnagar Abadi of 2022. Am I right? Yeah.
Right.
And he was speaking from Germany yesterday. And he
Right.
was so happy and to see such a good team of EICCRS people, not only the core faculties, but their adjunct faculties also, which we have in our team. Thank you, sir, for your such vision. I was a little bit nervous in 2016, how to start this click chemistry department, but you supported me, you boosted me, and yes, now the things are coming. Thank you so much, sir. Yes, on to Milan.
Hello, sir. I'm Dr. Milan Bera.
Right.
Thank you very much for giving me the opportunity in click chemistry to join here, and thankful.
Yeah, please. Yes.
Yes, sir. Yeah, now I can say, and thank you for blessing, and whatever Professor Mukherjee gave me the lab space and provided me the cabin. I believe maybe we'll do more from here. We can publish more publication, more research journal, patent from this our department. And we always expect so much blessing from you for further development.
When two fellows were to join, she was behind my life to make the cabins and lab, finish it by June. And so I don't worry. Before they come, it will be almost ready or fully ready. Am I right? You were every day reminding me, sir, my lab, my cabins.
Yes, sir. Yes.
Right. So, Manoj, I'm really proud. I know about each of your faculty. Every faculty I know, the whole background and research. Thank you.
Good evening, sir. This is Dr. Shruti Ahuja. I am the newest member of the Amity family. I just joined last month at Amity Institute of Biotechnology. First of all, I really thank you for giving me this opportunity, and I hope I'll do my best and justify the position that has been bestowed upon me by the Institute. And I really look forward to the wonderful years ahead in association with this great university, I can say that. Thank you so much for and keep blessing me so that I can put my best foot forward always, all through. Thank you so
Great.
much.
Very glad, very glad.
Myself, Dr. Mukesh Chaurasia, sir.
Right.
Thank you very much for giving me this opportunity. And we have various collaborations, research collaborations with Dr. Mona Lisa,
Right.
ma'am, and we might come up with some molecules maybe which is beneficial or drug molecule in near future. And thank you very much, sir. Thank you.
Great.
I'd like to state that Dr. Mukesh Chaurasia is really helping us. He's a bioinformatic person from Amity Institute of Biotechnology, and he's collaborating with us. As I said, that I love to collaborate with people, and we have so many adjunct people with us. And Dr. Mukesh Chaurasia's wife is Radhika Chaurasia, who has enrolled for PhD. And Professor Sharpless and John Moses was very happy to know that she got the suffix chemistry based functionalization of carbon quantum dots for targeted therapeutics. It was all over India. Only 2 students who are non-PhD who received this OSA project, and Radhika Chaurasia is one of them. So I take the proud moment to share this news with you. And Radhika Chaurasia is the wife of Dr. Mukesh Chaurasia.
Great, great.
Some of them are trained in Israel. Yeah.
Great. I read about him. Dr. Nalita, when you are going to now USA, are you meeting Dr. Sharpless, our Nobel laureate, Dr. Barry Sharpless?
Sir, that I have to ask. I need to talk to Jan Sharpless. Maybe
Right.
in this weekend I will talk to her if Professor Sharpless is in New York, or I have to see where he is. And then
Right.
we can accordingly plan. Of course, John is going to meet me on 20th. That's what he was telling. First, I should get the visa. I have applied for that. So first the visa should be.
Dr. Berry was to visit you and come to
Yeah.
India, but suddenly he got little
Yeah,
health
he got fractured.
problem and last minute he could not come.
Yes,
But I
yes.
told them that my people will come to your San Francisco place and meet you there. But
Yeah.
try to meet him because his wife likes you very much and he also knows you very much.
Yes, yes, yes. Jan is very good friend of mine. Yes,
Uh,
sir. And the last one, Dr. Debolina.
Devalina, I know you know that actually she got a very good job in the government, in the private organization at very good terms. And when I came to know, I told Devalina, I will not let you go. And she I will not say obeyed it. She respected my opinion. And I'm so glad, I'm so obliged to you. I have the responsibility for your wonderful future career because this lab of Ranbaxy formerly is head of that was Khanna. He was my class fellow in MSc in 1963 when we completed. So he was always laughing and we remember, but unfortunately died premature. But so I have visited also that lab that was formerly at other place. So I have stopped you from going there. So Mona Lisa, we have to take also care of her because she remained because of my request here. Am I right, Devanina?
Yes, sir. Yes, sir. Thank you so much, sir. You remembered everything, whatever happened before. Yeah, yeah. And that was the event, and that was thing that happened. And I want to thank you from the core of my heart. I'm here. I'm privileged to be a part of MET as well as this conference and all the events going these days. Like be a part of AICCRS.
Right.
I'm more than privileged and happy to be a part of it. So I want to thank you as well as all the faculties over here who gave me a chance to be a part of this, all the events and all the things which are going on.
Great.
Thank you.
Mona Lisa, can I hear one or two students?
Sir, that's the thing. Please, the students, please come in the front. All the research scholars. Rafia. Staff also. Yes. Please come here.
Hello.
Hello, yes.
Good evening, sir. Sir, I'm Suman Maji, PhD scholar. I'm now working under Dr. Devlina Ray
Right.
in CCRS department. This is my third year. So I'm now working in the synthetic organic chemistry.
Right.
Thank you all the lab facilities and all the permissions you have gave me. Thank you.
Right. Great, great.
Good evening, sir. I am Misbah Majood and I have recently submitted my thesis under the guidance of Dr. Mona Lisa ma'am, and
Right.
I'm looking for positions. Basically my thesis revolved on synthesis of carbon quantum dots and other nanomaterials plus hydrogels, and basically I have seen their effects on stem cells.
Right, right, great. Great, great.
Good evening, sir. My name is Swati Dhamija, and I'm working under the Dr. Ranjan Patra in
Right.
AICCRS department. And my topic is porphyrin catalyzed CN bond amination. Thank you, sir.
Great, great.
Good evening, sir. My name is Rafia Siddiqui, and I'm student of Dr. Ranjan Patra. I'm working in the field of supramolecular chemistry, and I would like to thank you for the lab facility and hope you do great work in future. Thank you.
Great, great.
Good evening, sir. I am Rahul Patil. I am working under Dr. Saikat Datta. My main field is single atom catalyst. metal organic framework and electrochemistry. Thank you for blessings.
Great.
Good evening, sir. I am Rupesh, working on the injectable and click chemistry-based hydrogel under the guidance of Professor Mona Lisa Mukherjee. Thank you
Great.
for kind of facilities. Thank you, sir.
Great.
Good evening, sir. I am Anbha Yadav. I am PhD scholar under Dr. Sekhar Datta, sir. My field is metal organic framework, single atom catalyst for the electrochemical and energy applications. Thank you, sir.
Great. Great. Great.
Very good evening, sir. I'm Hitesh Kumar Sharma. I'm enrolled as ICMR SRF in MIT Institute of Pharmacy.
Right.
But I am working with Professor Mona Lisa Mukherjee as she has provided me her extreme support in her department.
Right.
And the time I stays in AICCRS instead of AIB because they have given me all the facilities to work. I'm very much thankful to her and you for providing me the space to work.
Great. I know about you.
Yes, sir. Parmar is my external co-guide. And
Okay.
recently we have published one paper with Parmar sir and Mukherjee ma'am. And we hope we can do the good work. We can take this work forward for future.
It's not easy. It's not easy to get SRF fellowship or JRF. There's a hard competition. A large number of people apply and only few get this fellowship. I appreciate you.
Yes, sir. After my batch, government has shut down this scheme. I was the last one from maybe from MIT Universe who
Right.
got this fellowship.
Right.
Thank you so much.
I must tell to you all, after completing my MSc in 1963, I joined the DCM group organization, Rajasthan Vinyl and Chemicals. And our bosses gave us the job to develop a new catalytic agent for monomerization from monomer of PVC, polyvinyl chloride. And from the whole industrial house, my research was approved #1, and they started using this catalytic agent for monomer reaction. So from very beginning, I was only interested in research, right?
Good evening, sir. I'm Imansha Mishra. I am a DST Inspire Fellow and I joined under Dr. Sekhar Datta, sir,
Right.
as a PhD scholar.
Great.
A very good evening, sir. Myself, Diksha Mudgal. I am working under the guidance of Dr. Vivek Mishra, sir. And my research topic is metal dot magnetic carbon aerogel for the catalytic applications. So I synthesize the aerogels and I explore the catalytic activity of that. And
Great.
I would like to thank you and the ma'am and obviously Dr. Vivek Mishra, sir, for providing all the facilities and always supporting us. Thank you so much.
Great.
Hello, good evening, sir. Myself Isha, and I am a student of Masters in Molecular Chemistry. Thank you, sir.
Great. Where did you do Masters Molecular Chemistry? Where did you do your master's degree?
Yeah, I am pursuing Masters in AICCRS.
Okay, great.
Yes, sir. It's my second year here.
Okay, great.
Good evening, sir. Myself Malia Mishra, and I'm also pursuing Masters in Molecular Chemistry.
Great.
Thank you, sir.
You have a great future. All those pursuing in ACCR, a great future, I tell you, because we will be the front rider in this area all over the world. Then you will be known everywhere. So I'm very glad that you had the intelligence and wisdom to select these courses, these institutions. I'm very glad.
Good evening, sir. Myself Garima, and I have just completed my master's from AICCRS.
Right, correct.
Good evening, sir, and good evening, ma'am, and all of my teachers. And here I am joined as a PhD scholar in AICCRS department. Thank you, sir.
Great.
A few of our students are in the lab. There are some visitors, so they have gone just now. So 3-4 of them are there, and we have also good pool of part-time scholars who are
Right.
also working on Saturday and Sunday. They are
Right.
from Jubilant, Tewa, and other companies working with us. And also I would mention the name of the staff who has recently joined.
Right.
Yeah.
Hello, sir. Good evening. This is Jayashree.
Yeah.
Sir, I have recently joined with ma'am, and like I am a MBA graduate from Narsi Munji, but I believe ma'am is teaching me everything related to chemistry right now. So I guess I learn a lot, and with your blessings and with your blessing and ma'am's blessing, I believe I'll stay with Amity also a lot. Thank you, sir. I'm academic coordinator working in AICCRS. Thank you so much, sir.
Jayashree,
Yes, sir.
you must be a good person. I tell you why. I have not heard you or met you, but I brought one of my daughter-in-law, the son Ajit, who is going to be the biggest in the online in the world. So her name is also Jayashree.
Oh, thank you so much, sir. Thank you.
Great.
Yeah, people do tell me that how should we remember your name? So I tell them ki it's a very matlab Hindus mostly name Jai Shri Ram and all that. So you can remember my name.
You can tell as the name of the founder president daughter-in-law.
Okay, sir. Thank you, sir.
Great.
The last one, Dilip Bhatt, I should also bring him because he's a attendant and lab assistant who take care of the labs.
Right, right.
We should also give him a chance to talk.
Great, great, great.
सर जी नमस्कार जी।
नमस्कार।
सर मेरा नाम दलीप भट्ट है और सर मैं मैडम के साथ 7-8 साल से काम कर रहा हूँ सर यहाँ पे।
Right.
ठीक है सर, नमस्कार जी।
Sir, I must tell, when the entire after 6 o'clock or 7 o'clock, all the labs, all the departments are closed. This person is the person who waits for me, ma'am, aap kab jaoge? And sometimes then I have to tell, 9 baj gaya, aap Dilip ji jao. So I believe he should be also benefited with his career in Amity.
I tell you, lab assistant are very important. During my MSc, I had the best connect with my lab assistants, and they all ran to bring me chemicals and all whenever I needed. So lab assistant is a very important person. So Mona Lisa, some lecture is still to finish. Is some lecture still due, Mona Lisa? If some lecture is still to be held?
Done. Now we are going for the high tea, and then they will visit my department, see the labs, see the work, and then we'll depart for today.
Great. I think we should all give a big clap for Mona Lisa, Pooja and Saikat, and all faculty members. It's wonderful. And I think all my scientists, great scholars, great scientists, I'm so proud. I'm so proud.
Thank you so much, sir. Thank you so much.
So proud, and all these speakers have made our life a little more challenging, because I repeat, there were so many wonderful ideas in the lectures, and I ask Mona Lisa to make a note of all these points and who will follow it and up to what date they will start following it. Each point, at least there must be 25 research areas, what I heard today. Thank you.
Thank you, sir. Thank you. Thank you for your time, sir.
Thank you. Thank you.
Have a So it was very quickly organized. So we are coming to the concluding session of this international symposium on molecular chemistry and smart materials. How we have come forward with this idea that molecular chemistry was with us, yes, smart materials, because a lot of us are working in the area of materials. Yes, smart materials, because we have Professor Jan Kumar with us. He worked in the area of smart materials, and molecules and smart materials can go together. So that's why we quickly finalized the title, and Professor Parmar has agreed to that International Symposium of Masters in International Symposium in Molecular Chemistry and Smart Materials. I hope that you all enjoyed this from morning to the evening session, and we all have very nice talks, brainstorming sessions, the discussions, the questions, and I hope this type of brainstorming sessions and symposium should be there in future so that we can have a lot of ideas that how to go forward with research. So I thank all the participants, the guests and the students for making this day special. Thank you all and have a good evening. Before we end, let me give this mic to our honorable sir, that is Parmar sir, who is the honorary professor of click chemistry and part of click chemistry.
It's quite late in the evening, so I will not take a long time. But I sincerely want to thank Professor Mona Lisa Mukherjee for hosting all my colleagues here. And I'm sure that everyone liked this academically and socially also, the interactions. And these meetings are, of course, for science, but more so for personal context. And so that everyone is benefited, both the senior, I would say scholars like me, and the beginners in the field. So please keep up these interactions. And as Mona Lisa said, that we should have more opportunities and have such meetings. And maybe we can have one in January. It's tentative, but let us see how it goes. Again, good night. Thank you for being here. Thank you, Professor Mukherjee. And thank you, Professor Jayant Kumar, Professor Sunil Sharma, Professor Jha, and Professor B.K. Singh for really agreeing to come here and accepting my request in a short time, week or 10 days only. Thank you, everyone.
All of you, please join us for high tea. We don't have a cultural evening because it was fixed very quickly. So maybe in the long run, we will have some good cultural evening also.
We must thank the IT sectors who are in the always online, and we also thank the photographers who continuously cooperating the whole day program. And thank you all.